microphone's in my computer, and when I wander around the room, it'll get fainter and things. So like when I went to the back of the room, good luck hearing what I said. I talk pretty loud, so hopefully you'll be able to follow that. Okay? So, any questions on anything we have done so far? And like I was saying before you came in, several people have already started turning in the research paper topics. So listen to that part of the thing on. Oh, and where do you find that? You find those things on Blackboard. Okay. Now, are you familiar with Blackboard? Okay. Okay. You know, in Blackboard, when you get the home page of this course, there's a block up here with a number of tabs. In the instructor version of it, they're blue tabs. I don't know what they are on the student side. Okay? But one of those tabs near the beginning says Content. And if you click on Content, you'll see the syllabus is there. You can hear me talk about it on the YouTube video, or you can see it statically and not have to listen to me talk under that. Research paper instructions are there. Locator card is there. And I started loading your PowerPoints. I got chapter 1, 2, and 3 done. It would not load chapter 4. So I didn't have a chance today to go back and try again because I was setting up the lab, getting the lab runoff, setting up the lab, and also working on a test for another class. So I'll try to get that done. I doubt if I'll be able to over the weekend, so it'll probably be early next week before we meet again. I'm going to try to get those other PowerPoints out there. And I'll get the YouTube link out there. It's not there under content yet, but that's where it will be. So you'll see there only things through chapter 3 or 4, I think it is, and it just wouldn't copy. I think it's 4. It just would not copy anymore. So I'm going to try it with this computer. It's a little bit newer computer, and hopefully it'll work. Okay. Any questions? All right. Now, where we left off before, we hadn't quite gotten to the more math. That's the slide that's up there. But we were working examples 1.1 and 1.2, and we finished 1.1, did not quite get to 1.2. So let's do that one, or at least I don't recall that we did. A rock with a volume, let me get my pen set up. Okay. The volume of the rock is 4.50 cubic centimeters. Okay? And has a mass, so the mass of the rock is 15 grams, 15.0 grams. What is the density of the rock? We're looking for the density of the rock. Now, since a couple of you are new, let me go over this again. You might ask yourself, why didn't they just say 4.5 cubic centimeters? Well, they wanted to express that it was to the nearest hundredth of a cubic centimeter. That's how precise that volume is. It's not just 4.5 or 4.49 or 4. It's 4.50 to the nearest hundredth of a cubic centimeter. Same thing here. Not just 15 grams. 15 grams to the nearest tenth of a gram. This means 3 significant digits here, 3 significant digits here. And if we need to, we're going to either put 3 significant digits here or round to 3 significant digits. Now, capital V stands for volume. Later we'll see small v stands for velocity. Little m stands for mass most of the time. Occasionally we'll use a capital M, but usually that's it. I just put the subscript R here to let you know we're talking about the same rock. Now this symbol here for density, why they use it, I don't know, is a rho, which like an R in the Greek alphabet, and our alphabet is rho in the Greek alphabet. And that stands for density. Can anyone remember what the equation or the formula for density is? It's called the mass density. Mass over volume. And since we're talking about the rock, the mass of the rock over the volume of the rock. And what was the mass? 15.0 0.0 grams. And the volume of the rock, 4.50 cubic centimeters. And if you got a calculator, punch it in, see what you get. 3 point. Anyone got a calculator? Fairly close. I don't think that's it exactly, though, is it? 3.67 or something like that. Say again? 3.33. And on your calculator, it keeps going forever, right? But we round to 3 because we have 3 digits here, 3 digits here. So 3.33, that's just a number. Numbers usually don't answer questions. Numbers in units do. What unit? Yeah, grams per cubic centimeter. Look at them. There they are, grams per cubic centimeter. That is a good unit for a density, 3.33 grams per cubic centimeter. All right? Now, this book also has periodically some of these extra things in it. On this page alone, there are 2 concept applies. One is density, and they talk about the density of sharks and coelacanths, okay, very different things. But one thing that, if I'm not mistaken, the body density of a shark is actually denser than that of water. So therefore, in a sense, sharks never sleep. Because if they slept, if they stop moving, they're going to sink to the bottom of the ocean. And that's probably not what they want to do, okay? So no wonder they're ill-tempered people. That's my main thing, okay? And there's things about coelacanths as well. Then they talk about a dense textbook, okay? You could take the mass of this textbook, and then you could come up with a pretty good estimate of the volume. How? Say again? Okay. Actually, easier than that. Measure the width, the length, and the thickness. Length times width times height. There's your density. There's your volume. And the mass divided by volume would be your density. Now, they also have these little blurbs, which sometimes are pretty interesting, and sometimes I think, why did they waste the space on them? Myths, mistakes, and misunderstandings. Some people believe that tapping the side of a can of carbonated beverage will prevent it from foaming over when it's open. Is this true or a myth? And then they tell you how to set up a controlled experiment and try it. Okay, if you want to, you certainly can. We're not going to in this class, okay? In case it made a big, big mess, we're not going to do that. So that one, I'm not sure why they put it in here, but except to show, how you do experiments and things like that. Okay, next. We already talked about symbols and equations, and that was this section right here that we just did the problems out of, okay? But toward the end of that, there's this thing that the book is calling more math. Okay, does anyone need this on the slide any longer? Everybody got it? Okay. All right. This is what they're calling more math. This is on page 10, the right-hand column. Okay? We're going to talk about types of relationships. If you're driving from here to Tuscaloosa, what would you say the relationship was between the time you drive, the time that you're driving, and the distance that you have driven? Direct. Say again? No equation yet. Is those directly related or indirectly related? Directly related. The longer you drive, the further you go. Makes sense, right? That's called a direct proportionality. Okay. Now that term proportionality, I'm not sure, are y'all familiar with that at all? Or a little bit? Okay. Well, what that means is, here's how you would say that. the distance traveled is proportional to the time that you've driven. Okay? That symbol right there, it sort of looks like an alpha in the Greek alphabet. It also sort of looks like a goldfish, if you like goldfish, you know, or something like that. And that means is proportional to. That means it's a direct proportionality. Okay? There's another kind of proportionality. Oops, let me erase the other then. I thought it was further down the page. And that's an inverse proportionality. If you're driving from here to Tuscaloosa and you go at a certain speed, how is that related to the time it's going to take you? Directly? Inversely. Because the faster you drive, the shorter the time. The slower you drive, the longer the time. So that's called an inverse proportionality. Okay? So we can't have that. Now, how do we write that one? Velocity is proportional to 1 over the time. Or time is proportional to 1 over velocity. That's an inverse relationship. When one goes up as the other's going down, then you have to have one of them in the denominator, the other one not. So that's an inverse proportionality. Does that kind of make sense? Okay? Now, we have what are called proportionality constants. So let's go back to our first direct proportion. The distance traveled is directly proportional to the time that you drove. Okay? Everybody agree with that? Now, what you can do to make that an equation, alright, is it Alexis? Okay. Alright, does anyone else come in since I called roll? Okay. Let's see. It looks like to me, no, we're still missing Coco. Was here last time, not here this time. But others, everybody's here, and we've added to. What's that?
I think she said she get out of class.
That, yeah, I remember one of them did say that, so that must have been Coco. Okay. All right. So she may be a little later getting here. Okay. Now, how do you make the proportionality into an equation? Pretty simple process. Instead of the proportionality symbol, we put equal K, where K is some constant called a proportionality constant, K times T. Now, K is just used for any old constant, actually from the German word that means constant. That's where it's K, not C. But you know what that one is, don't you? What is the proportionality constant between distance and time? If you're driving from here to Tuscaloosa, distance would equal what times time? Distance is in miles. Miles per hour, which measures? Velocity or speed, exactly. So the proportionality in that equation, we know it. It's D is equal to, and you can use just about any symbol you want to for it. Some people use RT, the rate at which you drive. Some would use VT, velocity times time. You might even try to use S times time. S is used for so many things that I would tend to go either with R or V. It doesn't matter. You can name it whatever you want as long as you are consistent with it. So that's how you change your proportionality into an equation. Interject the proportionality constant. Okay? How about the inverse proportionality? There we had time was inversely proportional to the velocity. Okay? The time it takes to get from here to Tuscaloosa is inversely proportional to the velocity. Guess how we make that an equation? T is equal to K over V. Now we happen to know what that K is in that illustration. What would that be? Say again? It would be the same as velocity times time. And what is velocity times time? Distance. So that would be your distance. The distance from here to Tuscaloosa is fixed. It's not changing. It's not a variable. So therefore, this would be T is equal to D over V. Okay. Now, I'm guessing some of you have probably seen this next thing I'm going to show you before. I don't think we went over it in class. I'm teaching another physics class. I'm teaching 4 math classes. Can't remember which illustrations I've given in which class, but I'm pretty sure I did this in my other physics class, but tell me if I have. Let's just take this one right here. Distance is equal to velocity times time. Everybody understands that, familiar with it. Don't know if you've seen this before. Some people use triangles. I kind of like triangles. And other people use circles. Circles are fine too. They put a horizontal line through each, and then in the lower part, a vertical line. The horizontal line is a dividing line, and the vertical line is a multiplication line. Okay? The letter that stands by itself when you multiply is always put on top. Okay? And then the other two are put on the bottom. V times T. V times T. And you can get all 3 of your equations out of this symbol. Distance is equal to velocity times time. Velocity is equal to distance over time. Erase that one. Or time is equal to distance over velocity. Right, there it is. And it doesn't matter if it's a circle or a triangle, but there it is. Now, any of you seen that before? Yeah, I figured some of you had. I actually first saw it probably when I was in Navy, in the school, and I was in some course I had to take in the Navy. They were really big on it. They used it all the time. But if you can imagine, I bet y'all used it with Ohm's Law, maybe? Yeah, okay. Lots of electrical things follow this pattern. Distance things follow the pattern. Acceleration and velocity follows this pattern. Power and energy follows this pattern. We're going to see it over and over and over again. Just examples in this course. If that's helpful to you, use it. If you don't need it, you don't need to mess with it. All right. Any questions? So those are those. Let me go on and erase this, and this is just going to be repeating some of the things we've already said. Okay. Numerical constants. These proportionality constants that we just used were not strictly numerical, because one was a velocity, which has units, meters per second. So it wasn't just a number, okay? The other one was distance, which is some type of distance, like miles or kilometers or meters or inches or furlongs or whatever, okay? But sometimes these constants are just pure numbers. And the lab, I think we'll do today, you will be calculating one of the proportionality constants, and it will be just a numerical value. It arises because the units cancel each other out. And the other that we did, when you had velocity times time, time is in hours. Distance was distance, so your proportionality constant must be distance per time, so the time cancels out and you're left with distance. So those are proportionality constants with units. Some of them, the units actually cancel out, and you just have a pure number. Okay? Now, this is what I've already said. There's that symbol, proportional to. There's a little neater than mine. Okay? And if it says A is proportional to B, what that means is as B increases, A also increases. Why they have them on the opposite sides, I'm not sure. But as B decreases, A also decreases. Okay? Because they're directly proportional. To make it in, well, we'll get to that in a minute. Into an equality, you just interject a constant. Okay? Inversely proportional, that's the second one here. If A is inversely proportional to B, as B increases, A decreases. As B decreases, A increases. Because as one goes up, the other goes down. It's an inverse relationship. And there's quite a few things that follow those kinds. We'll talk about one a little bit later light intensity from how far you are from the source. Okay? I probably will tell this story again, but I'll do it. My wife likes to read, and sometimes after she goes to bed, if she can't sleep, she'll turn on a little reading light she clips to the book. That way it doesn't brighten up the room. I usually sleep through everything, so she is there. Would it work if she took that and just hung it from the ceiling? No, it wouldn't be bright enough because it's an inverse relationship. The greater the distance, the less the brightness of the light on the page. Inverse, and it's actually an inverse square relationship there. So we'll talk about those later. All right, so how do we make now this is going back, this is in pretty bad shape. If A is proportional to B, how we make that into an equation is interject the proportionality constant. This slide was put together rather poorly, but it's okay. Now it's an equal sign there, not just a proportional sign. Okay? So the proportionality can be replaced by an equal K. In any circumstance, that's what you replace proportionality with. And that's a direct proportionality. Here's your inverse. Well, it didn't show it, did it? Okay, there it is. I don't know why it didn't pick up the first time. There is the inverse proportion. Well, no, it isn't. That's not with the K. This is what we had before. To make that inequality, equal K. The K goes on top, not down here with the B. It goes on top. Equal K, and you have your equality coming out of the proportionality. It should have been there. It just didn't pop up. All right. Now, I think before we get to, and by the way, the concepts applied, this little blurb on page 11 in the left-hand margin, there's that inverse square relationship. Light, sound, many things follow an inverse square relationship. The further you are from a source, the dimmer, the weaker, the quieter, or whatever it is. Okay? And this gives you sort of an illustration of it, because most things, when I'm speaking here, my voice is really projecting everywhere. If you're right in front of me, it would be really loud, but the further you are away, you double the distance, and there's 4 times the 1/4 of the density of sound, because it's spreading in every dimension. And 3 times away, it's going to be 1/9 of the intensity, you might say. Okay, so that's what the inverse square relationship is. It goes as the square of the distance. Okay. They have a little blurb here on how to solve problems, and my guess is you've probably seen this in either math or science books all your lives. Okay, I don't know for sure, but I bet you have. And I don't necessarily say you have to follow these things rotely, okay? You can determine how, but a lot of these concepts are very important to do. You decide the order or which ones you're going to do naturally and which ones you have to remind yourself to do. The first is read the problem, okay? Don't just skim it. Read it carefully, read it 2 or 3 times, and as you read, or this is what I do, as I read, and I think I did it on that last one, I write down what they give me in the problem. Quite often, I'll also write down what they're asking for, and maybe put a question mark after that, so you know that's what they, I don't think I did that in the last one, but when they said the volume of the rock, I put V of rock. When they put down the mass of the rock, I put M of rock, okay? So I know what those symbols are standing for. So read and write. I do it at the same time, okay? They say make a list of variables with the symbols on the left side of the page. I don't care which side of the page you use. You know, just do it. It's okay, right? Okay. You're right. Okay. Yeah, I know you're in here somewhere. There you go. Yep. There it is. Okay. All right. Good deal. Okay. read the problem, start writing what your what they give you in the problem. Now, another thing I do, I think I've done this already in the class once. Yeah, I'm pretty sure I did last time. Draw pictures. Pictures are worth thousands of words. So draw the picture, and if you can see what they're asking for, usually you're better able to set it up to solve it, okay? Some problems don't lend themselves to that much, like the volume and the mass. There wasn't much to do there. When it was two masses on the table, then I drew a picture, okay, last time. Like I said, as you run across things, find what they're asking for. That's usually the answer to the problem, okay? That's what you're looking for. So give it a symbol too. What is the density? I put down rho for the density, okay? That was what the problem was asking for. So you identify all the variables that they mentioned and any that you're looking for. Sometimes you're going to have to create some in between, like you're missing a few things in between what they gave you and what you're looking for, and you may have to conjure those up, make manipulations to determine those. Other times they're looking for you to literally look it up. There's a physical constant page. Now, if you have the little book, I asked them to put this on the inside front cover. They didn't. They put it at the end of the little book, and there's a bunch of white pages at the end. You have to thumb through those, and then somewhere into the back of the book, you'll see that physical constant page. So you may have to look up some of the things you need, and usually those are listed. Okay? And again, I don't like their order here necessarily. When you're listing your data, do you just put numbers down? No. What do you put with them? The units. You've got to have the units there as well. Okay, now as you're listing them, if you see meters or centimeters per second or something like that, and then you have something else in feet, guess what? Not going to work. You're going to have to convert units so they're compatible. If you got a velocity in miles per hour, but the distance is given in kilometers, you got to convert. You've got to get your units all together. They mentioned that in Step 4. I like to look at that when I first list my data. If I see the units aren't compatible, I don't want to say, oh, I need to come back and change that later. Take care of it then. Okay. And then they'd already have write the equation, solve the equation, then they say substitute number value into the equation. I don't care what order you do it. I kind of call them plug and chug or chug and plug. If you know the formula, like we did for rho is equal mass over velocity, over volume, then if you have the data up there, plug in mass, plug in volume. That gave you density. But if you had that same formula, rho is equal mass times divided by volume, but they gave you rho and they gave you volume, then you're going to need to do some manipulating, multiplying, dividing, whatever, to get the thing you're looking for. Isolate that. And you can do that before you put the numbers in or after you put the numbers in. I don't care. Whatever you see and understand best, however you like to do it. Sometimes it'll be far easier to do one or the other. Other times it really doesn't matter. The book always likes you to manipulate the variables and then plug in at the end. You can plug and chug or chug and plug. I don't care which way you do it. You do the indicated mathematical operations, and I don't know if they say that here. When you've got the units there, again, the units must match, and your units are your friends. Because if you're multiplying miles per hour times time, hours, you're going to get miles. Yes, right. If you're trying to divide miles per hour by hours, you're going to get a totally wrong answer. You're going to get some type of weird acceleration. Velocity divided by time is acceleration. That's not going to give you a distance. And the units will tell you that. They'll make it very clear you've just done the wrong order of operation. Okay? So hang on to the units, let them help you in the process. And then, why in the world, and most of these things do that. Draw a box around the answer. I don't care if you draw a box around the answer. It does help me see what it is. And if you're really sloppy, yeah, I appreciate that. But if it's the last thing you do and you write down the variable equal this and have the units in place, yeah, I can figure out, yeah, that's their answer. Okay? So, they do give an example here, and the trouble is it's based on one they did before. Okay? But we'll do it. I'll try to make it much sense as possible. So let's go and do this. For an example, use the equation from the previous section, and there you have to turn back and get it. And I'm trying to find, okay, I think this is where the equation they're talking about. The volume of the gasoline in an empty tank you're filling is directly proportional to the amount of time the fuel was running, or in other words, the volume of gas is directly proportional to the time that you're pumping it. Okay, that's a proportionality. To make it an equation, you do V is equal to KT. Now, for some reason, they put TK. You can put it any order you want to. Well, what is the K there? Well, this is a volume. That's the time. Can anyone think what a good unit for the K would be? Trying to get volume over here, you multiply K times time to give you volume. So what must K be?
Price.
Say again?
The price.
Not price, the flow rate. So much volume per second, or volume, cubic feet per minute, liters per hour, whatever it is. That's your flow rate. Because if you're trying to get cubic feet here, that's the volume. Time here, cubic feet per minute, multiply by minutes, and you got cubic feet. So you see, units are your friends there. So that's what I'm going to call the flow rate. Okay? They're giving it in liters per minute. Okay? So let's assume the flow rate is 40 liters per minute. Keep up with your units. Okay? And most of the time they do use capital L for liters, even though it's not named after anybody. Anyone want to make a guess of why they would use a capital L rather than a small l? Cause what? Cause what? Say again? Length. Oh, yeah, it could be, but these are units, not a parameter. Is that what you said? Okay, but it's a good guess. What if I use a small l? Let me do that. 40 L per minute. It looks like a 1, doesn't it? So most of the time they will use a capital L for liters, even though that's not named after, it wasn't named after Fred Leader, so, or cheerleader, or whatever, okay. So most of the time we use a capital L there, okay? Now, and just like I was saying, units are your friends, so if the volume is measured in liters, then liters per minute times minutes is equal to liters. See, you treat units just like you do numbers. Cancel out if you need to. In fact, that is really a cancel. Now, if you had the flow rate in liters per minute, but you timed how long you did it in hours, is that formula going to work? Not until you change your unit here to minutes or this to liters per hour. You got to change one or the other. Or if it says how many cubic feet have you done, well, this will give you liters, but you still got to change the liters to cubic feet. So everything you do, you must have the units agreed. That's why you hang on to them. You don't just put down a number like they did in the Mariner probe, okay? It probed all right, crashed into the surface of Mars. Okay. So, let's go back to this. Suppose in the example that we just were saying, use the equation from the previous example describing the variables of a fuel pump. V is equal to, I don't like TK, I like KT, but I don't even like K. That's your flow rate. So let's give it a name that sounds like a flow rate. What do you want to call it? F, that would be fine. R would be fine. FR would be fine. So let's say the volume is equal to FT, where F is your flow rate. Okay? Now, predict how long it will take to fill an empty 80-liter tank. What's that a measure of? 80. What's that a measure of? 80 liters. That's your volume. Your V is equal to 80 liters. Okay? It says, I skipped over this order, predict how long it will take to fill it. Now that's sort of a sloppy word there. If I say how long, what am I asking? Yeah, in this problem it's time. But in another problem that might be how long, a length. So you have to get it from context. And this one is time. So how long, that means your T, how long, that's your question, that's your unknown quantity here. Okay? To fill the empty 80-liter tank, assume that the flow rate, F, is equal to 40 liters per minute, right? Yeah. That's a pretty easy one, right? How long will it take? 2. Yes, you better give me a unit with it. And how did you get that? You could. Now, here's what they're talking about. If you're looking for time, before you plugged any numbers in here, we could have said, let's divide both sides by the flow rate, and these flow rates cancel out, and you get T is equal to V over flow rate. This is what we're looking for. We knew this was 40 liters. This was, V was 80 liters. I'm not looking right. Okay. 80 liters, I slashed my zeros, by the way, if you hadn't noticed, divided by the flow rate of 40 liters per minute. Okay? So obviously 40 will go into 80. 2, the liters cancel out, and you're left with 1 over minute. Okay? That's a weird unit, isn't it? We'll take it off to the side. That's fractional forms, right? 1 divided by 1 over minute. How do you divide a fractional forms? Multiply by the reciprocal. That's 1 times minutes over 1. That's just minutes. So sure enough, this is minutes. Okay? So get used to manipulating your units. Is that a good time measure? Yes, it is. That sounds right. The units are right. It's reasonable seeming. 80 liter tank, 40 liters per minute. It's going to take more than a minute. It's only going to take 2 minutes. Okay. Make sure your answer makes sense. That's, to me, oh no, they did. They're step number 7. Ask yourself if the number seems like it makes sense. This is a really dumb example, but it really happened to me. I was teaching, before I started teaching here at Western State Technical College 21 or so years ago, I taught at Jeff State. I was teaching developmental math 090, okay? And there was in our homework problem set or something, there was this problem I gave the students, could have been a quiz or a test, and I took it out of their test bank or whatever, and it said, you went into the store to buy cookies come, 48 cookies to a box, and you went into the store and bought, and each box cost $1.19. Whatever, I'm making up numbers now. $1.19, and you bought 3 boxes. How much did you pay for the cookies? Okay? Now, the students were using age-old student practice of conserving every number they get. Okay? So, they gave 3 numbers in the thing. They got 3 boxes. They got $1.19, and they had 48 cookies per box. So, we got to use all those numbers, right? So, no, you don't. All you need is price per box times box, right? Units would have helped. Some of them multiplied by 48, and they came up with $90 to buy, or something like that, to buy 3 boxes of cookies. Others of them decided to divide by 48. So they got a fraction of a penny, was how much they paid for those cookies. Good luck getting out of the store paying for a few cents for 3 boxes of cookies at $1.19 each. What they didn't do is ask themselves, does this make any sense? They didn't ask that question. They just used every number I gave, and whatever the way they gave, they wanted to use it, and came up with a ridiculous answer. Don't give me ridiculous answers, okay? Make sure the answers make sense, okay? So, they go in gory detail and go through all those 7 steps again if you need to use them. Here's another problem, and this one we'll try to do a little more quickly, but I'll use it just like they give it in the book. Mercury is a liquid metal, one of the few liquid metals we have at normal temperatures and pressures. Of course, at U.S. Steel, they heat up to high temperatures, and most of their metals are liquid, but this is one at normal temperatures and pressure. So mercury is a liquid metal with a mass density. What symbol do I use for mass density? Say again? It was a long time ago. Yeah, I saw you write it in the air. A rho. And this will be rho for mercury. Now you may not know this, but the chemical symbol for mercury is Hg. So the density of mercury is 13.6 grams per cubic centimeters. Is that a reasonable seeming number? Very dense, much denser than water. Water is 1 gram per cubic centimeter. Really, really dense liquid. And is it reasonable units? Grams, mass, per volume, cubic centimeters. Yes, that looks reasonable. Okay? What is the mass? What symbol do we use for mass? M, little m. This will be for mercury. And it's asking, what is it? So that's your unknown. That's the thing we do not know. What is the mass of 10 cubic centimeters of mercury? What is that a measure of? Sure, that's the volume of mercury. Okay? So how do we go from here? Find a formula that relates density, mass, and volume. Oh boy, which one of the many that we've done? Oh, we've only done one. What is that? Second? Density equals mass over volume. There it is in living color. Okay? Now, one of 2 ways to approach the problem. Since you're looking for mass, you could multiply both sides by volume to isolate the mass. Okay? You could do it that way if you want to, and that gives you mass is equal to density times volume. Doesn't matter what order you do. And then you just chug and plug, you just chug, now plug in, and that's 13.6 grams per cubic centimeter times volume of 10.0 cubic centimeters. Cubic centimeters go out. How do you multiply 13.6 times 10? Move the decimal 1 place to the right, 136 grams. And that's a great unit for mass. So the units make sense. Yeah, that's a fair amount of mass. Now, didn't have to solve it first for mass up there. You could have plugged and chugged. In other words, density is equal to mass per unit volume, and plug in what you know. You know the density is 13.6 grams per cubic centimeter is equal to m over 10.0 centimeter cubed. Okay? Again, you're going to solve for the mass, so you multiply both sides by 10.0 cubic centimeters. Okay? Both sides. Okay? My writing is pretty bad. Okay? Cubic centimeters cancel out. Multiply 10 times 13.6, and you get 136 grams. Both of those disappeared, the numbers and the units. So that gave you your mass of that. You got the same answer. You did the same step. It's just one, you did it what they call literals, letters by letters, solved it literally, and then plugged in the numbers here. You plugged in the numbers and solved for the one you're missing. I don't care which one you do. Whichever you understand and see best. So 136 grams. All right. Let's move on. We've already done this slide. Okay. Now we're getting to the nature of science. This is the last part of this chapter, though it's several pages worth. Now, people could argue about this, but what today we consider science really hasn't been around too long. It started with these two characters here, Galileo and Newton. Before that, there were a lot of people who thought a lot of scientific stuff, but they mostly just thought about it. We'll talk about the ancient, they called themselves natural philosophers, which were largely scientists, but except they didn't do it. They usually just thought about it. One of the main ones was a guy named Aristotle. Way back BC, 300-400 years BC, Aristotle thought, he was a really great thinker, and he thought about lots of things, and he thought a lot of natural things, real world type things, not just philosophy, but real world stuff. And he came up with a whole bunch of rules just by his thinking through them, and nobody argued with Aristotle. So from then on, that was fact. Everybody believed it was true. Until along came Galileo. Now this was about 1500, something like that. 1400s, I think it was. 2,000 years later, okay? He said, you know what? This doesn't seem to hold water. So he would take what Aristotle had done, design an experiment, though he may not have called it that, to test what Aristotle had done. And if it came out right, okay, fine. If it didn't, there must be a different answer. That's when science was born. When you added that extra component, understanding based on experimental evidence. Not just thinking about it, but actually doing an experiment. Now, one unusual thing is both Galileo and Newton, and even up to Einstein, they did a lot of thought experiments. They did an experiment in their head, thinking, without actually hands-on, because some of the things they were thinking of were really tough to do physically, okay? But it wasn't just thinking about it, it was actually taking the steps through like we just did, and doing the experimental evidence as you went. Now, here's sort of an unusual thing about this. Galileo was an Italian, lived down in Italy. Newton, British, he lived up in England. And this is rather bizarre, it seems like to me. The very year that Galileo died was the year that Newton was born. Newton was born on Christmas Day, on the same year that Galileo had died earlier that year. Sort of like they did a cosmic, tag team or something like that, because Newton picked up on things Galileo had written about and carried them further. And that pair of them, even though they never, of course, met, didn't have any opportunity to meet because one was dead before the other was born. But they were so closely related, people think of them together. Okay? Different countries, different language, different everything. However, Back then, all scientific stuff was written in Latin, even though nobody except the Roman Catholic Church spoke Latin, okay, they did all the scientific writing in Latin. So they could have, and they did read each other. Well, Newton read Galileo's work because everybody knew Latin then, all educated people. Okay, so here's the scientific method. Basically, whether he wrote them down or not, formulated and first illustrated by Galileo and then just by everybody since then. Observe some aspect of nature. Aristotle did that. They all did it. That's where everything came from. Observing some aspect of nature, that's why I call them natural philosophers. Okay? Propose an explanation for something observed. Aristotle did that. He did it in spades. I mean, he did it really, really well. Proposing an explanation. Okay? Now, here's where he sort of fell apart. Use that explanation to make predictions. Well, what if you change this, or you did this, or something else happened? What would be the outcome? Okay? Test those predictions with experiments or more observations. See what happens. Okay? If exactly what you proposed happens, then see if you can refine it. If something else happens, go back and come up with a new explanation. Modify the explanation as needed, go back and test again. And really, science never ends, okay, in any shape or form. You always, in fact, physics in particular, along about the end of the 1800s, that's the end of the 19th century, the beginning of the 20th century, literally there were physicists who said this. You know, we've got our science all wrapped up, ready to go. We've got Newton's laws of motions. We have Lord Kelvin, William Thompson's thermodynamics. We have electricity. We have it all. We have all the formulas and equations, Maxwell's equations. We have everything pretty well wrapped up. We've just got to make a few little refinements, and then all it is, coasting from then on, teaching people, making them use good applications of it. We got it not. Well, there's these few little things, but we'll get those straightened out. Has anyone ever heard of quantum mechanics? Okay, that came along and blew the whole field of physics out of the water because everything was different. The more they found out that this just can't quite go the way you said it is, and for every new find they had about 3 or 4, 15 more questions. And then they had to start doing that. We still haven't recovered from that. So yes, they thought they were almost through and going to stop. We've modified as far as we need to. A few little nagging questions just opened up things, and now every question led to 15 more questions. So yes, nobody has it wrapped up yet, okay? Or even close. So, now I think this is kind of a weak example, but it is one. What are atoms made of? Okay? I don't know if anyone ever actually asked that question. They could have done this much better. A couple of generations before Aristotle, there was this other Greek philosopher, natural philosopher, that just did this thought. It wasn't really an experiment. He said, what if you had a piece of iron, okay, and you broke that iron in two, and now you have two pieces. Well, break the smaller piece and break it in two. And then the smaller piece there, break it into. It just keeps breaking down and breaking down and breaking down, breaking down until you can't break it down any further. That's the smallest bit of iron that you could possibly have. Now, he didn't have the technology to do that or anything else. He's just sort of that he thought through it and said, so let's call that smallest piece of iron that you can have an atom of iron. And the word atom means, in Greek, or it came from the word that means indivisible. Okay? So, that would have been a good place. Well, a couple generations later, here came Aristotle. And Aristotle, being Aristotle, he said, nah, I don't buy that. I think matter is a continuum. You can not ever break it to the smallest piece. It's always going to be no matter how small you break. So they threw out Democritus' ideas. No one came up with them again, okay? Until John Dalton came along, and he was studying how atoms or materials combine in certain ways, and they always combine in certain proportions. He said, well, the smallest piece of that proportion must be the smallest piece that that material could be in, and he resurrected that term atom. And he came up with the atomic theory. Why did they do that? They didn't know. Now, his idea, again, this is just an idea. And so let's just imagine that every atom has so many hooks on it, okay? And different atoms will have different numbers of hooks. And then you combine them, hooking the things together. Carbon has 4 hooks, oxygen has 2, and when you combine them together, you get CO2. Yeah, it works. Water has 1 hook, oxygen has 2. Combine them together, you get H2O. Yes, everything followed this pattern. Now, Dalton didn't think they really had hooks on them. It was just a model that he used to try to describe what he was seeing experimentally. Okay? Well, they didn't know why they did, but until someone discovered these negative charges, and someone came up with calling them electrons. And I can't remember which part of it. I think to name it negative was actually someone we don't usually think of as scientists until we think a little deeply about it. An American. He liked to fly kites. Ring a bell? In storms. Say again? Benjamin Franklin. He's the one that said, well, let's make electrons negative. Okay? So they did. And then the rest of it were positive. They thought the nuclei were positive, the electrons negative. So negative electrons orbiting around the positive nuclei. Now, there were decades of people contributing to this, but this is what they're using. Now, what they do is collide 2 atoms at pretty high rates of speed, and you see that you get electrons thrown off that are negative, and you get nuclei thrown off that are positive. So that's the experiment you did to see if you can produce that, and sure enough they did. Okay? But when they combined them, yeah, they got electrons off at higher and higher rates of speed, but then they found out they got some positive quantities and some that were neutral, that didn't have a charge. And then they realized that nuclei contains protons and neutrons. Protons are positive, neutrons are neutral, electrons negative. So, the new idea was atoms are made of electrons orbiting nuclei that are made up both of protons and neutrons. Okay? And there were lots of other pieces in this puzzle. So what do? They collide atoms at even higher energy. Okay? In fact, they have over in Europe, I don't know if you've read about it, it's actually so big, part of it's in Switzerland, part of it's in France, huge circular collider, and it's called the Hadrian Collider, okay? And they have done some really amazing experiments with that and seen objects, they think they have anyway, you don't see them, but you detect objects that are incredibly small, incredibly energetic, some that were predicted to have to be in existence, but no one had ever seen any evidence for. The one was the what's that guy's name? Higgs, the Higgs boson, okay? Have you heard of that? And anyway, he had predicted this decades earlier, but we just didn't have the technology to do it. When they built the Hadrian Collider, they finally produced something they think was the Higgs boson, okay? We haven't even talked about what a boson is yet. But when you make higher and higher energies of colliding atoms and other things together, you get all sorts of different things, and that's where they found out about bosons and fermions and all sorts of other things that are even beyond, smaller than the electrons, protons, and neutrons. Okay, so we're not going into all that. But that's just an example. The more we do, the more we study, the more we find out, the more questions there are to ask and to answer. So this is how science proceeds. And this is just a little dumb thing, but I think it was 2008 and 2009, my wife got her doctorate in public health over at UAB several years before this. And one of her classmates was, and a real good friend, was a grad student had come over from Italy. And he and his wife had just gotten married. We didn't realize it at the time, just a few months after Karen and I had gotten married. And they had started grad school, Karen and Fabio had. And then after they both graduated, Fabio got a job with a pharmaceutical company up in Boston. And he moved up there, and there, Rita, his wife, had their first child, Giacomo. We hadn't met him or anything. But then they moved back to Italy. We knew they had had a baby, but we hadn't seen them since then. And then over the years, we kept in touch, not all that often, but some. And then he got a postdoc back at UAB again. So he came and we got to meet him, and they'd had 2 daughters since then in Italy. And we got to meet all 3 kids and interacted with them for a year, had a great time reestablishing. And then they moved back to Italy after 1 year. And then the kids were in elementary school. I think Giacomo may have been in junior high or almost in junior high by then. Well, after several more years, Karen had some meetings in Italy, and it was right at Thanksgiving time. So I flew over and met her in the week we had off for Thanksgiving, and we went to Trieste to see Fabio, Rita, and the kids. And then by then Giacomo was in middle part of high school. Well, we got along really well with him, the girls too, but with Giacomo we just hit it off really well. And after that, they got the idea, since he was literally an American citizen born in the U.S., they wanted him to have the opportunity to either go to college in Italy or in the U.S. But they figured his chances would be better if he graduated from a U.S. high school. So they got to looking around various places and found there was a place, and especially when we interacted well with them, they looked in Birmingham and sure enough found a high school just up the road from where we lived. It's a little private school, and decided to send them there. So he lived with us the senior year of high school. And he was a real sharp kid. Even though he had a little bit of language issues and hadn't been on the U.S. system and stuff, he wound up having the highest average in his senior class, okay? He wasn't valedictorian because of the rules at the school where you had to be there 2 years to be at that, but still, sharp kid. Went back to Italy, Italy has 5 years of high school, so he graduated from an Italian high school too. Then he came back to the U.S. and we took him around to visit colleges, and sure enough, he decided to go, gag me, to Harvard, okay. Got his a degree in physics from Harvard, and then went back to Europe, and he was doing his research for his PhD at the Hadrian Collider in Grenoble, France. So, yeah, I talk about this, but I actually know a guy who worked there, Giacomo. Okay, too much of that. So, general scientific activities. Collecting observations? Yeah, the Greeks did that. Everybody's done that. Developing explanations? Yes, everybody did that. Okay? Testing the explanation? No. That's where Galileo, Newton, and just about everybody that followed them, that's where science began, really, is testing the explanations. And then coming up with new ideas. So let's look at some of these and procedures that we have with that. Explanations and investigations. They start with a hypothesis. Okay? We observe things, we think, do you think this could be the factor here? Let me give you different example. I'll give you a couple. When I was doing my master's at the University of Georgia, I was working with a guy in, believe it or not, soil fertility, and he was studying the effect of liming on soils and availability of nutrients and stuff like this. And so we did experiments that we would do different fertilizer and soil amendments and things like this to plots of ground. But we had to have all the plots being same type of soil, same slope of soil, same everything had to be as close as possible. All we did was vary certain things in different plots. Okay? So the hypothesis was that lime would affect the availability of the other nutrients. Okay? That's one kind, and that's pretty straightforward, obvious. My wife is a researcher at UAB right now, and she has studied she's an epidemiologist, that means someone who studies diseases, epidemics, you might say. And she has been studying a disease, it's a cytomegalovirus, okay? The odds are probably at least half of you have had the virus before and never realized it, okay? The other half will probably get it sometime in your life and never realize it, okay? It exhibits itself like a mild case of the flu or a bad cold or something like that over in a few days. No ill effects at all. Unless you happen to be a pregnant woman who contracts the disease for the first time or reinfects with the disease for the second time or later, and you pass that through the placenta into the fetus, in utero, and then the fetus could have from no effect to mild effects to serious effects to death. I mean, it runs the whole gamut. So she's been studying, she's not the only one. There's a whole team there at UAB who have been studying this. Several of them have retired already and made their careers studying this cytomegalovirus. One of the primary sequelae or things from it is hearing loss. And that's the one that Karen has been largely involved with. And she has studied how much of unknown hearing loss in kids could be related to cytomegalovirus, CMV infection, when they were in utero. And she's really come up with some pretty interesting results. She's had a couple of papers. She's first author in the New England Journal of Medicine, so she's up there, and has done really, really well with that. And the reason I'm telling you these various things, what is an experiment? That's not recreation, that's a recreation of an event or occurrence to test the hypothesis. Now, our experiments when we were doing the fertilizers and things like that in Athens or near Athens, Georgia, we, like we said, laid out plots. We put certain things, and here's what it's called: a controlled experiment. Like I said, we tried to control for same type of soil, same type of slope, same initial fertility of the soil, initial pH of the soil, everything we could to make sure everything was as similar as possible. Okay? And then what we did, we treated all the plots with certain things the same. The one thing we were studying, we put different levels on. Either none, a low level, medium level, high level. Something like that. Okay? That's a controlled experiment. Comparing two situations, all the factors alike except for one, the one you're studying. Okay? If it was lime, it was lime. If it was nitrogen, it was nitrogen. If it was potassium, whatever we were studying. Okay? Now, how Karen did it, you can't do that with kids. Okay? So what she did, she studied deliveries at the university hospital. Okay? And what she would do, and they had begun a test, they had grants to do this, to test all newborns at the university hospital to see if they were CMV positive or negative. If they were positive, that meant they had to have gotten, if they were newborns, they had to have gotten it in utero. Kids all, yeah. So then, but every time they had a child born that was positive, they would look back and find another child born within the same day or two, same gender, same race, same body weight approximately. They had parameters around that. So they were trying to measure control for everything they could, and then they follow all those kids. They tried to get 2 controls for every kid that was a case, and they would follow them. They would do hearing tests. They would do all sorts of things and measure how many. Remember, CMV didn't always produce a sequelae, okay? Sometimes it did. And other kids would develop hearing loss for something else. Maybe they had high fever or got an infection or something like that. So they studied this over several years. She looked back at records for several years, pulled out data, and found out some pretty interesting things. And since then, she's done other things. She's done flu studies and all sorts of things. But that's what you do in science. Control for as many things as you can, and measure the one thing, the experimental group that differs from the control group by that one influencing factor. And that's how you do science. That's how explanations. You start with a hypothesis. Okay? Her hypothesis was many of the hearing loss in kids that had been put down as unknown source were CMV related. And she did the experiments, and sure enough found out, I can't remember now, 60 to 70% of the kids that they had no clue why they had hearing loss in the study she did could be accounted for by CMV. So that just opened up a whole bunch of possibilities for people testing kids, early hearing loss, and if they had, and also checking the moms to see if they contracted CMV, and then they'd be ready. And as soon as the child was born, start interventions, because the sooner you can get to doing interventions, the more normal the child's life can be. If you start right away by realizing they had hearing problems, start immediately. And it's been pretty gratifying, the things they've come up with. Okay? Now this book is this author really goes a bit overboard in what he calls pseudoscience. What does that mean to you? What does the prefix pseudo mean? Anyone here ever heard of a pseudonym? Trying to think of one of the authors. I can't think of the woman's name now, but she wrote under put her as an author when she submitted manuscripts, initial, last name, and it wasn't her last name. And everybody assumed it was a man. And she got published, and she was very popular, and people were demanding her books. But no one who knew who this was until she came out later. I think J.K. Rowling may have done this, because she uses J.K. She doesn't list, and it was only after the books, Harry Potter books, became so wildly famous, she said, "That's me, that's a woman." Okay? And they just didn't believe it beforehand. Pseudonym is a false name. Pseudoscience is false science, which to me is a contradiction in terms. Science is truth, pseudoscience is not true. Don't even put the word science in there. So this is misleading or often absurd claims of scientific results. Remember when I was talking with you about your paper about the use of the internet? At least half of it is total garbage. Misleading, absurd. You can find anything to say anything you want to on the internet, and most of it's just totally not true. Okay. But unfortunately, some people have done this for science. And sometimes from some of the major research universities in the country. Because in order for people to make their careers, they have to produce. In universities, they often call it publish or perish. If you don't get so many publications in national and international journals, you get canned after so many years. Okay? So sometimes people will panic. Something they've been working on all these years, they keep getting not enough data to get the result, or actually the results come out different from what they were thinking, and they get nothing out of it, and after a while, they make something up. It hasn't happened often, but it's happened often enough. You have to be really careful. So what are some of the tests? Well, the first one, academic and scientific background of the claimant. Some of these have come from really good schools, you know. History of review by scientific peers. Well, that's how you publish papers. Every paper you read in a scientific journal has probably been reviewed very strenuously by at least 3 other scientists that were of equal or similar superior status, you might say. Participation in scientific institutions or organizations. You know, that's almost saying what we did here. Are they a member of a national laboratory? Are they a member of a major university? You know, you need to check this out. The claim published in peer-reviewed journals and independently validated by others. Now, not only does about 3 people review that, if it's something groundbreaking and new, before they publish it, they pick, say, 2 or 3 other scientists somewhere in the country or some other country, send them the procedure and say, do this and tell us what you got. They'll pay them to do it. And if they can't replicate the results, they won't publish. Now, unfortunately, a few of these have gotten published because either they thought this wasn't groundbreaking enough, they did that, and only later they realized it was made up. But that happens very, very rarely because most of the time they go through this procedure to keep it from being false science. Okay? That's probably too much on that, but he does the whole thing. So let's look at science in general. And this even is a little artificial. Okay? Laws and principles. Those are so closely related, it's hard to say which is which. Laws in general are important relationships observed to occur time after time after time. The law of gravity. You throw something into the air, it's going to slow down as it goes up, stop finally, and then come back down. It always does. Now, if you throw it fast enough, it may exceed like a rocket, you know, actually escape the force of your gravity, but that still can be measured. Okay? So gravity would be a law, the law of gravity. It's descriptive in nature, and when I say descriptive, that could include numerical description. Okay? Okay. Here's one. This is not me. This is someone whose last name was Charles. Charles's law, the relationship between temperature and pressure in gases. Okay? And later on, I'll do an arm-waving type thing of this, but no, actually that's volume and temperature in gases. But they're all related. Temperature and pressure in gases. I'll just give you a dumb example of this. When I was living, did my last degree at University of Nebraska-Lincoln. Pretty cold up there in the wintertime. And this was before I was married, and I was going to a church, and this lady at the church had a preteen or early teen young son. She and her husband were divorced. The husband was living in a different part of the state, a long way away. He had very little interaction with men, just women. He had a sister, he had a mom, he had, I think, a grandmother living. He just didn't have that, and she almost begged the church, somebody, can you spend some time, relating with some male role model figure. I didn't think I would qualify. I had no kids, wasn't even married, young. It made no sense until he came out and played on our church softball team. He was a really good athlete, and he was a little uncertain around the older guys there, and I kind of, dealt with him and encouraged him and that kind of stuff. We turned out, I thought, I may be able to do this. So anyway, I'd go over on the weekend and something like that. I remember it was fall or spring, I don't remember which. It must have been spring. He had left his basketball out overnight, and the temperature had dropped a lot like it did last night. I mean, pretty cold. And he went out on the Sunday afternoon, and it was still pretty chilly. He said, "Oh, man, the ball's flat. I'm going to have to pump it up." I said, "No, take it inside and leave it there for for an hour, we'll do something else, and then check on it. He thought I was nuts, but he put it inside, we did something else, and I said, well, you're on to do the ball? He said, well, it's flat. Go get the ball. Well, the temperature inside was much warmer than it was outside. Now the ball pressure was a regular thing. Gases, when they cool, the pressure decreases. When you warm them up, it increases. Okay? That wasn't my law, that some other guy in trouble. Okay? That is a law. It always happens. There's no place where it doesn't happen. Okay? So those are examples of laws. Principles. These are also descriptive in nature, okay, but sometimes a little more specific than the law. And again, the dividing line here is really fuzzy, okay? The difference is largely one of extent, not always a clear distinction. How many ways do they want to say this? For instance, some people will call Archimedes a principle rather than a law, okay? So it always works, but it's a little more specific. Does anyone know what Archimedes' principle is? Okay? It relates objects to fluids and buoyancy. Okay? And basically, when an object gets lowered into water, it is buoyed up, or it meets a force equal to the weight of the water it displaces. Okay? So if you take an iron ball and drop it into water, you can weigh it out here, and you'll see what it weighs. Drop it into water, it'll sink to the bottom, but if you had a scale there on the bottom of the pan, and it landed on the scale, and then you read that, as long as your scale would work underwater, then it won't seem to weigh as much, because it is displacing a certain volume of water, and that has a buoyant effect. We talked about that last time, didn't we? About Archimedes running down the street, that kind of thing. Okay. He determined whether the crown was solid gold or not, you know. He came up with that. Now that's a bit more specific than just the law. It's a principle and okay, now take that steel ball and heat it up and shape it into sort of a bowl or dish type thing. Same mass of steel. Lower that in the water, but now it's displacing more water because you have air in part of it. And after a while, that will float. Every ship in the Navy is made out of steel, which normally sinks, but it's hollow inside, so therefore it displaces enough water to get it to float. Now, submarines, they have one tank they call the negative tank. And that negative tank, they either fill it with water or they fill it with compressed air and force the water out. And when it's filled with water, then it sinks. That's how submarines sink. And then they blow compressed air into it, and that's what makes it come to the surface again. And that's called blowing the negative, is what we call it, because it's the negative tank. So does that mean force the water out, fill it with compressed air, and then you can rise to the surface? And they really want that tank to work right, okay? Otherwise, they're down there for the rest of the time. So those are laws and principles, okay? We also have theories and models. Okay, now theory is a broadly based set of those working hypotheses. You know, you put together several hypotheses, they're related to each other, and now you come up with a theory. Okay, it's always based on a considerable amount of experimental support, but you can't say it's become a law or a principle because it hasn't been around long enough or always been true long enough or whatever. So it's a theory. It forms the framework of thought and further experiments. And then you test something else. You test something else. You might ask why this would be. My wife's major professor at UAB, his big question he always asks, what's the biological plausibility for this? Yes, maybe CMV infections are related to, this was a dissertation research on sexual activity. Okay? Well, what's the biological plausibility? Does the virus cross the placenta? How does it get in? You know, there had to be some reasonable form there. Okay? So the theory, and that's what she tested over and over again. Now, models. There's not quite like theories. It's a collection of theories or ideas intended to represent a physical system. Okay? This was Dalton's hooks. That was just a model. He really didn't think necessarily that atoms had hooks on them. Okay? It was just a model that helped explain the situation, what he was seeing from the data. Okay? It's usually useful for regimes that are too small, like atoms, or too vast, like the universe, okay, for a direct observation. Okay? For instance, the Big Bang theory, okay? Or maybe that's a Big Bang model. We don't know, and we can't go back and test it, you know. In fact, now this may raise somebody's ire, but, you know, the theory of evolution. There's a lot of supporting documentation and experimental support that suggests it might be true, but you can't go back and test and see if you can start off with a couple of amino acids and make life out of it. That's just beyond us, okay? So that is and probably always will be a theory. Some people swear it's true, but no, so far it's just a theory. And the models are the same thing. Now, some of these models may be physical, like Dalton's hooks, which he knew probably wasn't the case. Others are mathematical. I mentioned, I think, earlier, Maxwell's equations. Early, and we'll talk about this a little bit in chapter 6, maybe. Early in the discussion of electricity and magnetism, people began to realize that, well, at first, you know, everybody had known about magnetism forever because they used lodestone to, you know, make compasses and things like this. I mean, we had been using those at sea for as long as we had been at sea, pretty much. But later, you know, the people discovered electricity. It started off being a parlor game. You rub amber with wool, and then you take it over and touch somebody and give them a shock, okay? And that was the extent that people knew of electricity. It was a parlor game, you know, you shock me, you know, and that kind of stuff. But then in time, people began to do other things and found out you could control and use electricity. And, you know, magnetism was increasing in its use and applications. And it was a long time, though, before people realized, hey, these are related. That a moving charge and direct current affects a compass needle. So there is some connection between magnetism and electricity. What that was, we weren't sure. And this guy named James Clerk Maxwell, spelled C-L-E-R-K, like Clerk Maxwell, but it's pronounced, he's Scottish. Scottish people pronounce things strangely, I think. So James Clerk Maxwell came up with, I think originally it was like 13 equations, but he boiled them down to 4 major equations that related magnetic fields to electric fields, back and forth and stuff like this. And he tied them together. It was a nice little model, a package, but at the time he did it, nobody had the technology to test it. So it was just a model, Maxwell's equations. About 70 years later, it seems like, they finally had the technology to really test these. And I think it was a guy named Heinrich Hertz, a German guy, who actually tested and showed not only did Maxwell have the right idea, he nailed it with those equations. No one's come up with anything better to tie those together. And he did it years before they could ever test it. So yeah, those are models. Sometimes mathematical, sometimes physical, sometimes just thoughts. Okay. Here's one. I hope you've had an opportunity to see a beautiful, beautiful rainbow, right? I can remember one time my wife's family, I was in the family by then, we were vacationing in Jackson Hole, Wyoming, because it's cheaper than Yellowstone, but we were staying there and going over to Yellowstone. And we were driving home one evening. It had been raining that day, and looking to the east, you just had this brilliant, this isn't a picture of it, but it looked a lot like this, brilliant rainbow. But then outside that, you see the dimmer rainbow? Have you ever seen those? Okay. What do you notice about that? I just gave one thing away. It's outside. Two things away. It's dimmer. Anyone notice anything else about that second rainbow? You might not be able to see it from where you're sitting. If you got the book, hopefully you can see it. Ooh, there's a blurb I need to come back to. Okay. Yeah, your book has a pretty nice picture of it too, looking at the other side of it, sort of. Anyone notice anything? The colors here, the violets and blues are inside, then the greens and yellow, orange, and red. But look at this one. On the inside, it's red, orange, yellow, green, blue. It's hard to see, but the colors are reversed. So the dimmer one's always outside the bright one, and the colors are reversed. What in the world could cause that to happen? Okay? And by the way, they're uniformly like that. If you ever have a chance to see a complete rainbow like that, they are. Okay? Now, I mentioned something else when we were driving along. It was late in the day, and the rainbow was to our east. And if you ever notice a rainbow, find the sun. You know where it's going to be? Behind you. Always. You'll never see a rainbow with the sun there or there. It's always going to be behind. You're only going to see them in the mornings or the evenings. You'll never see a rainbow, or much of a rainbow, in the middle of the day. Okay? There's some more observations. Okay? So here is the hypothesis. This is the result of the reflection and refraction. Now, those are two words we're not going to really get into. Refraction means bending. Reflection means sending back. You know, okay? Reflection and refraction of sunlight within individual raindrops. We call them a rainbow because they always occur after a rain. Okay? When there's little droplets of water in the air. So here is the model. Okay? Incoming sunlight. Now, if the sunlight comes in here into the droplet of rain, it goes right through. Okay? If it comes here, it goes right through. If it comes here, it goes right through. But right up here, at this angle, happens to be 42 degrees. The sunlight coming in, now, this is air out here. This is a water droplet. It's the water. Water has a different viscosity than air. It has a different index of refraction from air, so it bends the light. But because, and it bends according to the frequency, but because light is made up of multicolors of different frequencies, the red, the longer frequency, longer wavelength, shorter frequency, it gets bent less. The violet gets bent the most. So this is refraction of light within the rainbow. It gets bent to the back. Now, the reason the 42 works is that angle gives you total internal reflection. It just happens to be a characteristic of nature. Up here, it's going to go out. You know, most of it will go out. But down here, it all gets reflected. Total internal reflection on the back of that droplet of water. And at the same time, now the colors get reversed, okay? And they do again, and your observer, you see the rainbow here, okay? But you only see it at that 42 degrees. Well, the violet is here and the reds are there. because they get split. Okay? But more of the sunlight comes in here and it gets dispersed and doesn't get very well. But then right here, now this could have been on the top part or bottom part, they showed it here. Right down here, at the very edge of this thing, the light is getting bent again, and you get total internal reflection here, but then it goes up and gets reflected a second time and comes out, and this is at 51 degrees from the light coming in. 6 degrees beyond this. Okay? But you see a lot more light goes through this range here and makes this a brighter rainbow than just a little bit of light that goes through that very little bitty portion of the droplet of water that gets bent twice, and that's the dimmer rainbow. And because it's twice, it reverses its order here, but then reverses back again, so it comes out in exactly the different order, opposite order from this. So there you have it. The sun has to be coming from your back, has to be. You're not going to see a rainbow looking into the sun. You're not going to see it at noon because now the sun's coming down, okay? You'll only see it when the sun's behind you. And all this, by the way, the center of this, wherever it is, 42 degrees here, 51 degrees there, okay? That accounts for the phenomenon we see. Yes, yeah.
The reflections have a reflection.
What's that?
The reflections have a reflection.
Do reflections have a reflection? Yeah, this one is a double reflection. It gets reflected here and back here. This one doesn't. It only gets reflected once and comes out. So this one gets reflected twice because that critical angle that here, it hits that at the same angle it comes out. Anything in between, there's interference. And that's why you get nothing here. Is that what you were asking?
No.
No.
So, well, yeah, kind of, but you see the reflection of the real rainbow? The one right there, like that.
Okay, every rainbow, is that what you're asking? Does every rainbow have a second one?
No,
Oh, that's
just
not
an
right.
example. Like, you see the yellow rainbow right there?
Yeah.
Yeah. You think they got a reflection?
Is that a reflection of this one?
No, do you think it has its own reflection?
Oh, does it have a third one out there we just can't see? I don't think so. I think you run out of room on the water droplet. And you run out of the backside of the water droplet to get the reflection.
Yeah,
I think,
basically on like any kind of reflection.
yeah, but they only occur at that one angle that's called the critical angle where you have total internal reflection. So you only have one here at the, not really the fat part, but a portion of the droplet, and then you just barely have room in a spherical model to have that second internal reflection. And that's why it's reversed. That's why it's much dimmer. I still don't know if I answered your question, but yeah. Okay. All right. Those are just a couple. I did skip some things when I was turning the pages. I always try to turn the pages to things that are not in the slide set we still get to talk about. There is a nice little blurb on page 15, basic and applied research. Now, basic research are some of the things like Einstein did or Maxwell did or some of these dudes. It's pretty heady stuff. It's just looking at the very nature of being, you know. Whereas applied research is in taking some of that basic stuff and then how can we use this? For instance, has anyone heard of superconductivity? Okay. There are, silver is the best natural conductor of electricity and heat, by the way. The same thing, we'll talk about this later. But why don't we use silver in wiring our houses then? Way too expensive, plus it's pretty brittle, hard to do. Copper is almost as good as silver, but not quite. But copper has the advantage of being cheaper, but also bendable, okay? So it's easy to bend a wire, you know, and stuff like that with copper. It'd be very hard to do it with the silver wire. So it has some advantages. Now those are the two very best conductors. After that is probably aluminum, but it's not nearly as good as either one of the other two. Actually, during World War II, when we were making an awful lot of brass shell casings. Now, why are shell casings made out of brass? Anyone know? It doesn't respond to magnetic fields and stuff. And you don't want suddenly to be a charge if you have ammunition, then it could just explode. So brass is used in the shell casing. Bullets, the shell casing is brass, right? Okay? And you just don't want them conducting something that they shouldn't be conducting and setting off a charge. Well, brass is made out of copper and zinc, I think, or something, but copper's in there. So during World War II, when we were making ammunition, even before we got involved in the war, we were making it for Britain and France and everybody else who was on our side. And then later we got into the war, and then we were really using it. So copper got very short supply. All of it went to the military, and houses that were built during World War II, largely they wired them with aluminum, with not copper. Are there many of those around? Why not? They burned out, okay? Because the aluminum wasn't as good a conductor and heated up, and then we catch things on fire. And unless they were retrofitted after the war and rewired with copper, most of them would burn, okay? They just shortage and things like that. So, where was I going with this? Conductivity. I don't know how many Nobel Prizes have been won on this, but somebody discovered that some really bizarre material, when lowered to a low enough temperature, suddenly became almost no resistance at all. They're called those superconductors. They were oxides, they were all sorts of things. Things that weren't great conductors at normal temperatures suddenly became superconductors at very low temperatures. That was basic research that discovered those things. Discovered superconductivity. Discovered the materials that made that. That was basic research. But then people came along, well, how do we use this? There's a really cold temperature. Well, the Japanese have done a really good job of it. Have you ever heard of their bullet trains? They have trains that travel across the island of Japan. It's a pretty small country, really dense and stuff. Those trains go at enormously high speeds. Almost as fast as planes. How they do that, what prevents all trains from going very fast is friction. Okay? You just can't. The airplane doesn't have much friction. Air resistance, yeah, but not much friction. Well, what the Japanese did was take superconducting material, even though it took a lot of energy to cool them cold enough to make them superconductors. When they're superconductors, that means you have almost infinite current, no resistance, and if you've got it going through coils, you get magnetic fields. Again, the tie between magnetism and electricity, and those trains can literally sit off the tracks. They don't sit on the track. They're repelling, and they glide over the track, so you have almost no friction whatsoever. Okay. So that would be applied research, is how to take the basic research and put it to something useful there. Okay. If you went back to my wife's stuff, the thing, basic research would be how that virus does cross the placenta. Is there any way to stop that? Any understanding of that. But then applied research, well, then can we come up with a drug that will prevent it from crossing the placenta? There's all sorts of ways that applied is basic. So that's what they're talking about here. There's some questions there. If you find that of really interest to you, you might want to do a paper on that. I'm not saying I would, but you might. Seekers of pseudoscience, I think he overdoes that, but you can look at that if you want. There is a blurb on page 17, figure 114, we're going to talk about in a later chapter, so I think I'll hold off on that one. Then there's a rainbow. Here's another, I think I'll turn, okay, I'll use this. Have you ever looked at a globe, especially the Atlantic Ocean, and noticed how similar things are on either side of the Atlantic Ocean? Here, South America bulges out, that's Brazil, in there, whereas Africa bulges in. The North America slants this way, Europe slants that way. Same type thing. This part here almost looks like it should fit into the Gulf of Mexico and the Caribbean. Okay? Someone noticed that way back and came up with the idea, the theory, the hypothesis, that maybe those fit together at some time way, way in the past. And the other scientists said, are you crazy? Continents don't drift. They don't move apart. Continents are fixed. It just happenstance they look the same. Well, since then, we have discovered there is a ridge in the middle of the Atlantic. And that ridge has seismic activity going on all the time. It has magma coming up from the surface and building a ridge there because there's underwater volcanoes all along that. Because sure enough, continental plates, they call it plate tectonics, they do move. That accounts for earthquakes, volcanoes. What's the Pacific called? You know what it's called? The edge of the Pacific. Johnny Cash sang a song. Ring of Fire, exactly. Okay? He wasn't singing about the Pacific, but it's a term. And most of the most active volcanic activity is around the ridge of it. Why? Because the Atlantic is spreading apart, meaning the Pacific has to be coming together. And where the plates are crashing together, that's where volcanoes, earthquakes, and things like that happen. Think of some of the most recent plates. China, Indonesia, a lot of them have been out there. Now, some are in other places as well, and we'll hear about those near us sooner, but some of the big ones have been there. Alaska had the biggest one on record, last I remember, okay? Ring of Fire. Now, every chapter also has a little blurb like this, okay? This one happens to be on Florence Bascom, okay? A geologist, studied rocks and things, and she, I think, probably contributed in some senses to our understanding of plate tectonics. It's been a while since I read this. I think that's what it is. The reason she's mentioned here. Guess what? Is that your source for your paper? No! The book can't be your source for your paper. It can be the source for your idea of the paper, but you have to go somewhere in the literature and find your source. You can't use the book as your source. Okay? You can get ideas from the book. You can write a Florence Bascom, but it better not be this material here. Okay? I've read this. I'll recognize it. So you have to go outside the book to get that. Okay. We are at the end of the chapter. There is a summary. Now, this summary is reasonable length. It's a fairly short chapter, but a lot of the key words are in italics. I don't know. I think all of them are. That's how they do. Then there's a summary of equations. We only ran into one. Okay? So expect to see this equation in one of its many forms on the test. Okay? Or you're applying that equation on the test. Okay? There's key terms. Now, this key term is a pretty long list for such a short chapter, but it's given alphabetically, but the page number where the term originated or was first defined or described is listed there, so it makes it easier. There's applying the concepts. Now, this chapter may be a little less than most. Most of your tests are going to be multiple choice. These applying the concepts problems are all multiple choice, okay? There's 44 here for this chapter. That's a little on the small side. Most of them are closer to 50. but some of them are maybe a little smaller, and a few maybe quite a bit bigger. But they give their answers too. So that would be, on most chapters, one of the best things to study for the test. This chapter, it won't hurt, but not as many questions will be. And it's not going to be the same questions ever, but it'll be the same type of questions, same concept being done. Then there's questions for thought. There happen to be 10 in this chapter. That's a few fewer than most chapters. For further analysis, there's 7. That's more than most chapters, okay? And then there are some parallel exercises at the end that are a lot like the examples we did as we were doing it, coming through the chapter. So those are probably worth it. In this chapter, probably that's your best thing to look at. Now, for those of you with the little books, I gave mine away before I remembered to check on it. I hope they put the Group A answers in the back of that book somewhere. If you got the thin book, not this big one. This one I know has it. The thin book, in the back of the book, are there answers for the parallel exercises? Somewhere near the back. Huh? I asked them to put it in, but I guess yeah. That's the last. That's from the last chapter. No, I bet you that's what these 20 pages are. Sorry about that. They didn't put the answers in. I asked them to when I made the order. They said, sure, we can do that. And then they gave you a bunch of blank pages. Sorry about that. If you do need to see answers for those, you can take pictures of mine, or I can go make copies on the Xerox machine. So, or whatever, copy machine. All right. Any questions on chapter 1? Okay. We've got another 25 minutes before lab time. We do have a lab on chapter 1. And for those who weren't here, let me say this. This is the longest, most involved lab of any lab we're going to do all term. Hate to do that to you on the very first lab, but that was what was in the book for this one. We'll deal with many of the concepts that we covered in here, even though it's the shortest chapter we were doing, had a lot of concepts in it. So that's what we're going to be doing in lab. Hopefully we'll get it done in 2 hours. If not, we'll take some time in the next class to finish if we haven't had a chance to finish that. And then next class, the last 30 minutes, we will do the test for chapter 1. And again, this test has a few more calculations than most of the chapter tests will have. It will be a little shorter. There are only 10 questions, but there's multiple parts of the questions. Most of the chapters will have tests of closer to 20 questions, but I just found the test bank really nitpicky on this chapter, so I adapted the questions that were good, and so it's a little bit different type of test. More calculations, and some fill in the blanks, and some just a couple of multiple choice. Most of them after this will be multiple choice, mostly multiple choice, a few calculations, and 1 or 2 fill in the blanks. So prepare for that. All right. So if there's no further any questions on chapter 1? All right. Now, we're going to have a break at 3:45 because we'll move to lab, and we can stop a little before that, so we'll have plenty of time for lab. But does anyone need a break right now? If you do, we can take a little break now. You do? Okay. All right. While I'm getting set up, then try to keep it less than 5 minutes, folks. I'm going to start in less than 5, so try to be back by then. All right, we are now recording again, and now we're going to start on chapter 2 as soon as the projector does light up. Any of you come up with any questions from chapter 1? Okay. Okay, chapter 2 is entitled Motion. Now, in some physical science books that I've taught from before, this would be broken into 2 or 3 different chapters, okay? Most of the time, describing motion is a chapter, and explaining motion is a separate chapter, and then some applications of motion might be in yet a 3rd chapter. This one is all clumped into one chapter. So whereas the first chapter was fairly short, this one is quite a bit longer. Okay? So, chapter 2 is motion. The core concept here, and if you have your book and watching it, it's on page 25. Pretty short statement. A net force is required for any change in the state of motion. Okay? Now, there's several things we're going to have to define before we understand the full ramifications of this. Number one, what in the world is a force? And what do we mean by net force? Okay? Is the force exerted by a fishnet? No, that's not what they're talking about. Okay? And what do we mean by change? We'll talk about that. In a state of motion. What in the world is a state of motion? Motion, we kind of have a feel for. What do we mean by a state of motion? And then further, what do we mean by change of the state of motion? So those are things to look for. Well, first question, what in the world is motion? And this is basically the breakdown of the chapter. We're first going to, like I said before, describe motion. These aren't in even thirds, but the first portion of the chapter will be describing motion. Then will be another fairly big portion will be explaining motion, and then the applications of that motion will be the third part, a little bit on the shorter part of the chapter. So that's what we're going to do, but we still haven't said what is motion. Okay? So in order to describe motion, we're going to go with three basic concepts. First is the concept of position. And so say I'm right here. This is my position. Let's say I move to there. Move, motion. I have to move to get to there. So that is going to involve, number one, some distance that I moved. Okay? And number two, it took me some time to get there. So position is generally measured in distance terms. Okay? Now, there's another concept that's pretty close to distance, and that is the one of displacement. I displace myself from here to there. Okay? The amount of that I did, that's the distance. The displacement, what makes that different from distance, is a direction. Distance is what we call a scalar quantity. It's just how far. Displacement is how far in what direction. And we're going to do that on many of these terms. In fact, one coming up right here. Speed. Okay? I said two things were involved, distance and time. So if I measure the distance I've traveled plus how long it took me to get there, distance divided by time is speed. Okay? But displacement divided by time, which has direction involved, that's velocity. Now in everyday English use, we use those two words like they were synonyms, right? Speed and velocity, right? In physics, they're not. Speed is a scalar quantity. All it has is a magnitude. Okay? And basically it's never negative. It's just a magnitude. Velocity, on the other hand, is a vector quantity. Direction is involved. It has the same magnitude as the speed, but now you have a direction with it. That direction may be this way, or it may be this way. Okay? So that's two different directions. Same distance, so the position change is the same. The speed might have been the same, but the velocity, one was in that direction, one was in this direction. We'll get a little more detailed with that later. Now, we'll hit this later, but I'll give it to you now too. Position, time, two different quantities. The time rate of change of position, distance divided by time, that gives you speed or velocity, depending on whether it's displacement or velocity, distance or speed. Okay? Acceleration is the time rate of change of velocity. Okay? So that's your good old 0 to 60 in 4.3 seconds, right? That we talked about last time. Someone made it up anyway. Okay? So acceleration is time rate of change. So distance or displacement, time rate of change of that is speed or velocity. Time rate of change of velocity, that's acceleration. And we'll do this throughout the course. We'll define a new term, and then somewhere along the way we'll take the time rate of change of it. Okay? We do that with forces, time rate of change of momentum. Power is time rate of change of energy. You know, we'll just run into that over and over and over again. Okay. So that's sort of the first part of the chapter, the basic concepts describing motion. Now, some of the applications of this in describing motion, this isn't the applications at the end of the chapter, this is in the first part. We will do horizontal motion. It says on land, wherever you are, you can do it in a room, whatever. Horizontal motion, and then we'll do falling objects, which is vertical motion, and then we'll do compound motion, which is two-dimensional motion. We're not going to get into three-dimensional motion. Those really get a little complicated. We'll stick to two-dimensional motion, which most of our motion really winds up being that anyway. Okay? We will have one lab that's going to deal mostly with this, which is not strictly horizontal motion, but it's one-dimensional motion. Okay, not horizontal always. And then another lab we'll do, which is the compound motion. We won't have one that's strictly just falling objects. So in compound motion, you have falling objects as well. So we'll do the second lab we do the first one today from chapter 1. But then the first one we do from chapter 2 will be measuring velocities and acceleration. And then the lab after that will be doing compound motion. And then the third lab will do some of those applications at the end. Okay. A little bit of explaining the motion. Okay. So the second part of the chapter is in explaining the motion. And the basic ideas here are forces, and we've already had that in our core concept. I think I've already mentioned to some extent, but maybe not. I think that was my physics class I taught last night. Inertia and mass and how they're related. And then the big way of explaining motion is Newton's laws. He came up with 3 laws of motion that basically revolutionized. Do you need to be? Okay. Okay. You think they're in here?
They're not.
They're not. Okay. Should they be in here? I've got the roll. Who is it? Who? Lacey? I think so, not this guy. L.
Yeah, we're just kind of doing this walk around.
Okay.
They're going to show you the message too.
What's that?
You give this too.
Okay. Okay. See, that's one of those examples that I was giving you. Sometimes we need phone numbers because they're trying to find the student, you know, and they don't have a way to get in touch with them. Okay? So that's Newton's laws. And then the third part of the chapter is in applications. And we'll talk about momentum and impulse. Both of these are pretty pertinent things to many of your lives. Okay? Circular motion, definitely that leads to Newton's law of gravitation. So Isaac Newton is in on all this stuff. And we'll talk a little bit about our satellites and other things like that. So that's the third part of the chapter. So let's go back to motion, how we measure it, what are the things involved with it. First concept here, 2 fundamental components. I just mentioned them. What are they? In describing motion? Distance and time. Okay? The 2 fundamental components, distance and time. Change of position, that's distance. And if you think back, remember the basic units that we had? The first was length, another one was time, and then there were others in there. Here we are dealing with 2 of those fundamental components. Change of position, which is a length measure, okay? And change of time. Now notice here the common word is change. For motion to be happening, you have to have a change of position, and it has to take a time. I mean, I know in Star Trek, beam me up, Scotty, but it still took some length of time, It was never immediate. It can't be immediate, okay? Now, we will talk about instantaneous rate of change, but that's coming up later, okay? Here's an illustration of this. If this car was traveling down here and did 1 mile every minute and consistently did that 1 mile a minute at 0 minutes when you started the car and started the stopwatch, or the car passed to this place here, and that was at time t equals 0. 1 mile later, it was at time t equal 1 minute, 2 minutes, 3 minutes, 4 minutes. Every time it was passing a mile marker right then. What can you tell me about that motion?
60 miles an hour.
60 miles an hour, because 1 mile a minute, since there's 60 minutes in an hour, that would be 60 miles in an hour if they maintained it for a full hour. Absolutely. Okay? And it's constant then, right? Because nothing is varying. It's a constant rate of change. Okay? So, time, distance. You need them both to describe motion. Okay? Now, 3 important combinations of that length and time. Okay? We've already mentioned all of those. Okay? The first of these, now we mentioned displacement or distance, that's just change of position. Okay? But the combination of that with time, one of these is speed. Now, I've already mentioned it. What can you tell me about speed? It is just a magnitude, okay? A scalar quantity. Just has a measure. And usually, it can be any kind of units. Centimeters per second, millimeters per second, miles per hour, kilometers per hour, furlongs per fortnight. Anything, distance over time. Distance over time. That's what speed is. Direction doesn't matter because it's a scalar quantity. It's just a magnitude. Okay? The second is velocity. Same units. Miles per hour, feet per second, meters per second, centimeters per second, miles per minute. Whatever you've got, that's your velocity, except velocity has a direction with it. To the northeast, to the south, up, down, whatever, it's going to have even if it's straight line motion, it's positive if it's that way, negative if it's this way. It has a direction. Speed doesn't care about a direction. Velocity is the speed at a given direction. It's a vector quantity. Speed scalar, vector, velocity. Notice the letters are even the same. That's just happenstance, but that's how I have to remember. Okay? And finally, we have acceleration. Now, how does that differ from the others? Speed is the time rate of change of distance over time. Velocity is time rate of change of displacement, a vector quantity, divided by time. What is acceleration? Yes, the time rate of change of velocity, actually, because it is a vector quantity too, so you need velocity for it. So acceleration is the time rate of change of velocity. So this would be meters per second, miles per hour, whatever. This would be meters per second, miles per hour, whatever. This would be meters per second, miles per hour, per minute, or miles per hour, per second. Change of velocity over time. Now, when it's meters per second, we call that meters per second squared. There's no such thing as a square second, so don't think of that. It's just meters per second. It's easy to write meters per second squared. Okay? It's just a unit being divided twice, so you call it squared. Okay. Any questions on that? All right. I think probably we need to stop there, and we'll pick up with the speed slide next time. Okay? Didn't do enough to have any real homework or anything for you. So let's just go over it. Right now we're going down to the lab, 253, just right down the hall here. First door on the right. And we're going to do the lab. Now, it's going to take me a little bit to set up. Like I say, this is the most complicated lab we have. I got all the materials in there, but because I was afraid there might be a biology class coming in, I didn't want them messing with our stuff and losing it, so I put it all in one place. As long as there's not a biology class in there, that's where we'll do the lab for today. Like I said, it will take me a little bit to set up. So I know you just went on a break, but if you want to take a little break, you can. But 253 is where we'll go. Unless there's a class in there, and if there is a class, then I'll have to find another room. So that's where we're going to be, as far as I know. And I'm going, okay. I got to call roll again. Remember, I have to call roll twice a day. So I'm supposed to do it at 3:45, but we're not quite there yet. Okay, I'm going to take my computer too, so I'm going to pause it here. All right, now each of the tables, pause. Okay. You can start reading the first part, ratios, and what we're doing first is part A on the front page. Circles and proportionality constants. Remember those? We talked about them in class. Okay? Now, I've given each team 3 sizes of circles. All of you have a small circle. All of you have a big circle. 2 of them look like this. One of them's that cup right there, the top of the cup. And the other one has, And then the medium-sized circle is, hold that up, is that one. Now, some of these are cracked, so don't break them or anything, because that's your medium circle. Okay. Now, what I want you to do, you have 7, and 6 people in a group, okay? So to start with, on that blank piece of paper, and you have extra sheets there too if you need it, each 3 people from each group. One will have a small, a medium, and a large circle. What you need to do is exactly what it says in number 2. Mark the diameter on each circle by drawing a straight line through the center. So in other words, you take the piece of paper I gave you, and put the circle down, and with a pencil or pen, I don't care which, mark the circle. Then with the ruler, I gave several rulers to each group, you'll measure, I would suggest let's see if it says, in millimeters. Now these rulers all have millimeters. That's the little fine side here. Don't do the inch side, the centimeter side, but each one of the little spots in between the centimeters, that's a millimeter. Okay? So measure the diameter of the circle in millimeters. You draw one circle, measure its diameter, pass it to someone else in the group, preferably someone who has already drawn one. Okay? So 3 of you are doing that. When you draw the circle, measure the millimeters, pass it to somebody else. So each group, catch this, each group will take 3 measures of each circle. 3 different people will measure each circle. Each one of you measure 3. You measure until each circle has 3 different measurements by 3 different people. That's where we'll begin. Okay? Now, where you put the measure, turn back to page 23. Okay? And what you're calling these are trials, a small circle will have 3 people, different people from each group, measuring the diameter. And you put that in millimeters. Now, if you're not sure how to do it, ask me. Don't assume. Ask. Okay? And pass it around until you have 3 of the small circles, 3 of the medium circles, and 3 of the large circles. Each one of you will draw maybe 2 circles and measure diameters. You may not all have that. Yes? Okay? No, those are centimeters. No, you're right. Okay? Okay? All right, the way that looks now. Okay, the millimeters, you see there's 10 in each mark, 10, 20, 30, that'd be 140. Okay.
So when you're saying all of us measure it, what if it's the same? If it's the same.
Okay, wait, yeah, don't try to get the same measurement.
No, I'm saying if it is, though.
It is fine, it's perfectly fine. You're measuring the same circles. But once you've done that, pass it to somebody else. Not your piece of paper, they've got a piece of paper, there's plenty of paper around. And that circle.
Okay.
Yeah.
And I do the circle.
And you do the circle too. And each team will do, the team does 3 circles. You don't do 3 circles. You won't be doing more than 2, most of you. Okay? All right.
That's definitely
Have you done one yet? Okay, we'll let him do that. The most that any person will do would be 2. Some of them may only have to do 1. You're in groups of 7. Because there's 9 measurements. Yeah. And even you, I think, yeah. You have 9 measurements. 2 of you, 3 of you all only did 1. Yeah. Okay. The diameter. The longest is right now.
I just put a little more.
3 of the small, 3.
Oh. Someone has a ruler you're not using? Yeah. Can they borrow it? Yeah. Wait just a second. Okay.
So I'm ready.
Try to get it. That'll be 139. Yes. Who asked the question?
1,000.
From here to there. Yeah. Any other questions? Okay, once you've got 9 measures of your diameters. Everybody got that yet? Okay, y'all remember, y'all are one team.
Right.
Y'all are one team. So y'all are sharing data. Okay? We'll only do 3 per team of every one. Some of you only have, several of you, half of you, more than half of you only do 1 measurement. Okay? The others will do, a few of you will do 2. No one should be doing 3. Okay?
That's the medium. Who got the small?
Has anyone got all 9 diameters measured yet? The whole team.
That's
kind of small.
Okay?
Oh yeah, they do it like that.
Any team got all 9 diameters yet? 3 small, 3 medium, 3 large.
If you got 89, that's 890, right?
Yeah, 8.9 would be 800. Right, okay. Okay, where are you measuring from? Right here. Okay. Put the 0 on it, okay? And then do it. 8.9, that would be 89. What that was?
So I got 90.
Now, always try to get a diameter, which is the longest distance crossing.
Okay, I see why I messed up.
In 1 centimeter.
Well, you hit that right
I messed up.
Or you can count. Any team got all 9 diameters? Yeah, you should have 9. 3 small, 3 medium, 3 large. Share data with each other now in one team.
What you doing drawing size? What you doing drawing size?
Has anyone finished all 9 diameters? 3 medium, 3 small, 3 large. Share among yourselves. Now, none of you should have been doing all 3. Okay? At most, you should have had 2. So, in the whole team, that's 3, 3, 3. Not each individual. Not one table. The whole team, 3, 3, 3. I bet you've done 9 already. You haven't?
41.
You did too?
41.
We got 40. We got 42.
Look at the off there, buddy.
I would start from scratch and draw your stuff.
Number 2.
That's why y'all had lots of paper. Okay, any team got all 9? What's that? You got 7 people in your team. Several of you have done small, several of you have done medium, some large, several large. 1, 2, 3 small, 1, 2, 3 medium, 1, 2, 3 large. I know you've already done the measurements. You had to have. Share data. You're on the team. Okay?
Medium, I got 8. How y'all get 8?
No,
How
man,
y'all
where
get
did you get 18 from?
How y'all get 18?
I ain't been to 18.
I didn't think so.
89. It's 89.
I didn't write that. 89.
Surely, y'all have got 9 measurements so far, right?
Yes.
All right, good. All right.
We just got to get them broke down now.
If you haven't got 9, you can wait and get those in a minute. I'm going to show you how to do a circumference. That's a lot trickier. Okay? Now, what you do, if you can take the same device that you did before, I need a device, but that's the big one. Okay. This will work. Okay. Hand it here, and all of you look on. Okay? What you got to do with the circumference, and for some reason these have got stiff and hard. Okay. Go around the base, and this one's tough because it's got curved edges. Okay. Go all the way around, keeping it somewhat tight. It's almost more of an art than a science here. You might need to help each other out with it because this is being really stubborn here. Okay? Okay? Run the string around until they cross over here. And whoops, don't let them get underneath either. Until you get them together. And when you get them together, then spread it out. And with your, here you'll probably, for the big ones, you'll need the meter stick. And again, you measure in meters how many millimeters you have. Okay? Each team has a meter stick. So each one of you do one, either small, medium, or large. Pass it on to someone else until you have 3 circumferences for each one. Don't multiply 3 for each one. No one will do more than 2. Okay? Hey, and there's plenty of string. Don't be waiting. Here's the circle not being used. Okay? There's 3 circles, several strings. Good. You'll need the big string for the big circle. You who have this one, yeah. Millimeters. The circumference is also measured in millimeters. Okay.
So that's the middle one?
For the moment, I'm going to pause the recording. Okay, the teams have measured their diameters in millimeters and their circumferences using the string in millimeters, and then they're getting ready to do their ratios. For each team, 27 cubes. Okay? Now what you're to do is first verify the cubes. Measure in millimeters. I think, let me see the lab. Oh, here it is. Here's mine. Okay, you go back to your instructions, which are Part B, area and volume ratios. Obtain 1 cube from the blah, 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 blah. Note it says 6 sides, 6 units surface area, blah, blah, blah. Overall size. Okay. Okay, it doesn't specify. Again, I would use millimeters, but if you want to use centimeters, you can. But I would use, if you use centimeters, it's going to be a decimal point. Millimeters will probably round to 1 unless you can guess what fraction of in between. So measure this side, and that side. Measure all three and see if they're the same. They should be. You might do that on several of the cubes. They should be the same size, right? So on the first one that you choose, measure length, width, and height. If they're the same, what's the surface area of that? Say again? What's that? Length times width, that would be some area, times
The number of faces.
how many faces?
Yeah.
6, exactly. So that would be your first one, okay? That's the small one, small cube. You do surface area, and be sure you're using millimeters or centimeters. Centimeters, you're going to have decimals. Millimeters, you probably have a whole number. Okay? And then how do you get
all of them?
Huh? Yeah, oh yeah, just take a cube. Use cube. Now y'all have to get together. Don't need cubes. But you don't have enough measuring sticks, so yeah. Okay. You only have so many rulers, so measure the length, width, and height. Surface area, measure length times width, multiply those two together, multiply by 6, you get the total surface area, right? How do you get the volume? How do you get the volume? Length times width times height. So multiply those three together. That gives you the volume. Record those under small cube. Now, y'all are one team. One team here, one team there. Make sure you got numbers that are compatible with each other. If you want to do them separately, you can, but make sure they're close. I don't want scattered all over the place.
These are small.
What's that? All those should be about the same. They should be the same. Okay. So that's a small cube. Just a single one.
That's 9 times 6. Whatever. 6.
We gotta put millimeter square, right?
What's that?
Millimeter square.
Yeah, the surface area is millimeters squared. Volume is millimeters cubed. Plenty of squares and just not that many rulers. So just make sure you got something you all agree with. You don't all have to do it separately.
Do we have a size split?
They should be. That's why. That's just verify.
They're all
that.
about the
They should be the same.
So what it was, you got medium.
Everybody has a small cube done?
Oh, sure. Like make 2 of them.
Okay. You got plenty of A few rulers and we got plenty of cubes, so they should be the same. So compare notes. And decide on what measurement you want to use. All right. The teams did a single block, length times width times height. That's a volume. Length times width is the surface area times 6 would be the total surface area. Then they did 2 by 2 by 2 blocks. So they doubled the length, double the width, and double the height. That'll be the volume of a 2 by 2. The medium block, and the surface area is the length times width. Area times 6 would be surface area. And then finally, 3 by 3 by 3. Take the length times width times height, that's the volume. Length times width times 6, that'll be your surface area. Okay? And you do the ratios. Surface area to volume. Part C, okay, it says obtain at least 3 straight-sided rectangular containers. Unfortunately, these are not straight-sided, okay? So here's how you're going to approximate the straight-sidedness. Okay. All right. Y'all looking?
Yes, sir.
Is everybody finished the ratios of your cubes? Yes. Okay. So, obviously this side is a little slanted. So how you deal with that is, and by the way, let me see the statement here. These are measured in centimeters, not millimeters. Centimeters. Okay? So go from the middle of that to the middle of that, and that will approximate. That's a little long, that's a little short, so if you do the middle, you'll have a good approximation. Make sense? So the middle of that to the middle of that, that's your length, there's your width, do the middle always, and the height, try to get something as close and do it that way. So that's going to give you your volume of your box. Okay? You got 3 different size boxes. Okay? So y'all can be doing those measurements. Did y'all get a box? Yes, he's got the box. And they've got a box. Okay? Now, let me just say this. This will be, I think, a little help. It really doesn't matter. But if you wanted to, number 1 is going to be this box. Number 2 is going to be that box. Whoever has, yeah, that one. And number 3 will be this box. Now you're sharing data within the groups. Okay. So you're doing only your box. Your lab does that one, you do that one, you do this one. Okay? So you're doing your measuring and recording that. Now, here's the scales. We only have 2 scales, so y'all will have to share among the 3 groups. When you're finished recording, by the way, and you'll only be recording for your box, okay? And it'll be helpful if you keep the boxes in the right order. Your number which? 3. Your number which? 2. Your number 1. Okay? So you put your length, width, and height of your box in the right column. And if you want to, you can go and calculate the volume. And then at some point, you need to determine the mass of your box, right? So when you have gotten the other thing done, you come over here to one of the scales. Now notice, folks, you first zero the scale. Line up the 0 with the thing before you put the box on. Okay? I'm going to let you zero it. Zero the scale, then put the box on. And now, okay, listen up. Every one of these little bitty lines here is 1 gram. So when you see 10, that's 10 grams. 20, 20 grams. And the little things in between, each one of those is a single gram. And they're sort of long one, short one, long one, short one. Each one of those is 1 gram. So when you, be sure you zero your scale first, and then take the mass of the box. Oh yeah, if you need paper, oh! I didn't mean you turn in that paper. Usually it's best to both zero it, the same person zeroes it and measures. Okay, hey, here's the deal. You see, if you look at a different angle, you'll see a different number. So whoever zeroed it, wherever he was standing, that's where you measure it at. Okay? There's 2 scales, 3 boxes. Get them at, determine. Okay.
What is it?
You feel like 30 grams?
Yeah, it was.
30 grams?
Oh,
You said.
right?
Now don't tear up bones.
You plant them bones over there. Don't go eating on it.
Now I'll tell you how.
This how big man is. He didn't tell us that part.
That's why I picked up the paper, you remember? I didn't want that cycle. What I suggest you do, no, you don't want to wet jacket?
It's waterproof, but I don't want to wet.
Okay, now, wait. Put your container on. Come on.
You fill it up with water.
And fill it up with water. It should still be 0.
Yes, I do.
Okay.
I was not too, but then I thought about that.
It's 30.
Yeah, you'll later share with the other groups. Yeah. If you want to now, you can be getting the dimensions of the box. You can do that now. You've been the small group. Small group, here's your water because you have a smaller box. You do have to fill it.
That's fair right there.
What we got? 45, so it's 45 grams.
That's hell of that.
Okay, what you get? Okay, now, what you do next is pour the water from there, without spillage if you can, into here.
Tyrell.
Okay. Thank you. Yeah, the paper towel's right over there. Okay. Which one do you think you don't need to put it.
I got my skeleton, buddy.
Okay. Warmer now, okay. Yeah. You got the mess with the water, right? Well, no, you got the mass and the water, and you got the mass of the container. That's right.
Okay, I was going to say that's 1,500. The whole thing.
Okay. Now what you need is the milliliters of water. So this is a little awkward to do this way, but this is what I suggest. You only use that much.
No. No. Supposed to get more than that?
Huh? No, okay.
I had more than that.
Okay. No. All right. Sorry.
Okay.
Okay, don't get ahead of me, folks. Okay. If you want to come see what this team is doing, they've got the big container. So come see and watch, and you'll do it with your two small containers. Okay? Okay, can everybody come see? Come see, come saw. Okay. Y'all want to see it? Y'all want to do it right? Come see? Okay. You want to have to redo it? Stay where you are. Okay. Y'all here to see? Oh, okay. Come on. Okay. Okay. Now, I think well, maybe not all of you have done this, but what you did, zeroed the scale, right? Then you measured the mass of the container alone, right? And then they took their container of water here and poured it until it was absolutely filled, right? Measured the mass of container and the water, right? Okay? Then they took that, and I say use this one. Whoa! There was my container. Okay. All right. Okay. Then this was empty. Pouring that in here with minimal spillage. Okay. Now take this, and because this doesn't have a lip, I emptied all this water out. Okay. And then pour this back in here. Okay. Get it all in there. Okay. And then pour this, because this does have a spout. And don't overfill the graduated cylinder here. Okay? I'll let you do it. Okay? Don't overfill it. That's as far as you can measure, so don't get past that. If you need more, then take a second graduated cylinder and don't overfill it. They had the big one. They have to worry about this. You have smaller ones, you only going to need one graduated cylinder. Okay? So you want and this is measured in milliliters. Okay? And that's what you put down in number, what is that number? 8. Okay. Let's get, Tanika, you're in the group that's back there. Here's a lab for you. You'll have to get to the rest of the day and your lab teammates. Okay? Let me get a new one. Okay. Now. Very good teamwork. Whoa, 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 whoa. No, I'm just kidding. 178. What? Y'all through with the scale? Yeah. Okay. Y'all need the scale?
Yes, sir.
Okay. You understand what to do. First, you zero the scale, mass of the container, and then did y'all ever get to?
Stand for the. We got to pull this out. We already get the.
Where's the little container? There we go.
They're making the same container.
Huh?
Put in the same container.
Yeah. Okay. No, when you threw the water in, okay. This is water you pour. Now, you don't think it's water.
Are you sure?
Just dump it all out. Okay.
There, that enough.
Let your hand
That's massive water, right? 160. Do I do that? Now, massive container in water, 178 under 6. You calculate 7 by subtraction. Number 8, measured volume of water under number 2, 150 milliliters. You do the rest of the calculation. Group number 3. Someone got all the data? Okay. All right. Let's see if I can read. Yeah, I can't do it. All right, I'm going to sit here so I'm close to the thing. Number 3, groups 1 and 2, listen up. Length of the container, number 1 under 3 is 16.5 centimeters. Number 2, the width of the container under number 3, 8.75 centimeters. Pretty precise, huh? Number 3 under number 3, height of a container, 3 centimeters. All 3 of those are 3 centimeters. You calculate number 4. Number 5, mass of container, 30 grams. Number 6, mass of container and water, 485 grams. You calculate number 7. And then number 8 under number 3, measured volume of water, 440 milliliters. You calculate the rest of it. Okay? Any of you have any questions how to do those calculations? Any of you miss any of the data? You got it all? Okay. Any questions on the calculations? Pretty simple. Number 4, multiply the 3 numbers above it to get cubic centimeters. Number 7, subtract the number 6, subtract from that number 5. That's straightforward. Number 9. Okay? Number 9 is the ratio of volume. That's 8. No, I'm sorry, calculated volume. That's 4 divided by measured volume. That's 8. 4 divided by 8 on each of those 3. Okay? Yep. And number 10, ratio of mass of water. That's 7 divided by measured volume of water. That's 8. So 7 divided by 8 on each of those. Okay. Now, has anyone got everything done so far? Yes. Okay. Then, you should have done everything that's down through number 5 on page 17, right? Yes. Following your mass and volume things. if you flip the page to number 6 at the top of page 18, make a graph. And you'll find out that most of these labs that come out of the lab book, they love graphs. Okay? So make a graph. Mass in grams, that's the row 7 data, and the volume in milliliters, that's the row 8 data, to picture the mass per unit volume found in step 5. Okay? So don't worry, that's the step we just did, dividing. So put the volume on the horizontal axis. Now you decide how you're going to orient this. Frankly, it doesn't matter because the numbers are very similar. But give me your, your data. Okay? You're looking at these two here, 7 and 8. Okay? All right. In general, it looks like your 7's a little bit bigger than your 8. This one's smaller, but these two are a little bit bigger, right? Okay? It doesn't really matter. So therefore, and that's the mass. Okay. So I would, with the data you have, I would orient it portrait. No. Yeah, portrait. Okay? And number here, this will be mass on the vertical scale, volume on the horizontal scale.
Volume.
Volume on the horizontal scale. Okay? As it said here, make a graph with, put the volume on the horizontal scale and mass on the vertical scale. Okay? So what you'll do, what I would suggest, have 0 in the corner here, and you're going up to how far? Volume. 455. That's mass. 440, right? Okay. Your vertical scale, let's do this one. 1, 2, 3, 4. Okay. What I would do then, 0 in the corner, okay, on the horizontal scale, which is mass in grams, 100, 200, 300, 400, 500. So you won't use the last two blocks, right? Going up, 0, 100, 200, 300, 400, 500. You won't use the top 4 there. Okay? Did everybody follow that? Right? Okay? Volume on the horizontal scale, starting at 0 on the bottom left, 0, then the big dark line, 100, 200, 300, 400, 500. You go most of the way across the page, not all the way. And then going up, 0, 100, 200, 300, 400, 500. You don't use the very top. Okay? Now you do your ordered pairs. Okay? And the ordered pairs will be, for the little container, number 1, you'll use number 7 data on the vertical scale. At the same time, you're using 8 data on the horizontal scale. You'll come up with a point. Does everybody understand that? Okay. Have you finished calculating? No, that's that first.
What are we going off of?
What's that? All right. Okay, let me see your data. Yeah, so you got about the same. Okay? And we're doing mass on the vertical scale. So do a portrait model here. Mass on the vertical scale. Volume on the horizontal scale. Okay? So, yeah. Okay, it's 8.7. Yeah. So vertical is 7. Okay? And the scale list, 0 in the lower right, lower left corner, 100, 200, 300, 400, 500. Going up, 0 in the lower left, 100, 200, 300, 400, 500. Okay? This is mass upward, volume horizontal. Everybody see and understand that? Yeah, okay. So you did yours this way, right? Okay, that's fine. That's perfectly fine. You got plenty of room both ways. Okay? So for your horizontal scale 1 vertical 96. Okay. Horizontal 8. Horizontal 1. Okay. Actually, this would be 110. 101 just past 190.
Oh yeah, I just concentrated mine on
3 dots. Actually, you could have a 4th dot. What if you had a container with 0 volume and 0 mass? That could go in the corner. If it helps you, use it. If not, just go to the 3.
Is that what we're at?
Let's see. Okay? Your points may be right, but the line you draw connects the
Oh, it
point.
needs to be like that.
Yeah.
Oh, okay.
Okay? And if you need to, you can use 0, 0, because if you had 0 mass, you'd have 0 volume, right? So if you want to, and get the best fitting line, that's why I use these see-through rulers. Best fitting line to do. So you don't need that dark line up there. But that's
So you
not
just go to 0 for this one.
if that fits the other 2 points well. And it's awful little there. Just do the best fit you can. Play around. Draw a straight line. Okay.
Some other ones.
Anyone got the point plotted yet? Yeah, that's why you gotta have a see-through rule. And draw your best straight line. Y'all need another one? You have 2 there. Anyone not using the ruler? There's another ruler. Okay. Y'all gonna keep yourself busy with that for a little bit? Help each other out. I'm gonna haul some stuff down to the lab so I don't have so much to do later. I'm gonna pause this for a... Alright. I'll say it again here. Okay, once you've answered you calculated number 8, the slope, and fill that in on page 18, then you subtract that, or subtract 1 from that. It can be either a positive or negative number for number 9. That's your experimental error. Then you answered questions 10 and 11. 11 is completely up to you. You just have to answer it, yes or no, but then why or why not. Okay, then results 1 through 7 on page 19 and 20. And then problems 1 through 7 on 20 and 21. Understand, the block that you see in figure 2.4 on 20, it's the same block you'll have at number 3 on 21, except then you list the dimensions in centimeters, not meters, and calculate the surface area of each of the faces, and answer the rest of those questions based on that. Then you should already have the rest of it filled out, your data. What's that? All right. Anyone anticipate any questions in the next 5 minutes? I'll certainly be willing to answer them. Think not?
So we got test Tuesday, don't we?
Test Tuesday. That'll be the last 30 minutes.
On
That's
chapter
why
1.
On chapter 1.
Can we kind of do a little review before the test?
I'll answer any questions you have.
What's the test going to consist of? All chapter 1, I know.
Yeah, chapter 1, and it's largely going to be that formula, the density formula.
Yes, sir.
That's going to be a lot of it in all its various forms. Calculating one thing or another, answering questions about it. But you also have things that we did like, given one thing, calculate.
Yes, so how many calculations?
Yeah, this will have more calculation than any of the other tests. It'll also have some short answer questions, so
Yes, sir.
be familiar with it.
Maybe just go back and watch all the videos. We should be good.
Yeah, I think that would be good too. I don't have the link yet, but hopefully I'll have it by Monday. North Carolina, or you just have a shirt on?
Oh yeah, from North Carolina.
Where?
Charlotte.
Charlotte. Yep.
The border between where we live, the border of South and North. So we live in Indian Land, South Carolina. But then my parents worked in North Carolina. So my brother being a
Oh, you had to be.
yeah, I like ever since I was little, I like colors and all that. So it was always that, you know,
Good luck on your test.
Right.
we do in North Carolina. So every time
I thought you were talking
said,
about
"Oh,
this book. Yeah, those are. I rented those on Amazon for like $50.
No, but then
Always
every
look
time
on
he says that,
Amazon.
North Carolina.
I don't like
But
the
yeah,
books.
we go sometimes to Charlotte, we go to Augusta, Chapel Hill, where, Notorious play. So, actually for my birthday, we got to see, the Blue Devils and Tar Heels in action.
Oh,
It was actually for my early birthday party. I was like, I can't find it.
Right.
So,
I was actually born in High Point, but my family lived in Robbinsville.
Yep.
But my mom was working for a doctor who he operated, or that's who she went to see, and he did his deliveries in High Point. So we went to High Point.
We always wanted to go to Boone and Appalachian State to go skiing and all that, But we just,
Yeah, did you have a question? I don't know.
Oh, this homework, right?
Huh?
This homework, right?
Yeah, it's just, we're gonna finish that, do all you can, and we'll do some in class.
I appreciate it.
see you later.
But this will make both you and your brother mad, my father and my uncle at NC State. So they're both back.
Yeah, there's NC State, Duke Blue Devils,
And Wake Forest.
Wake Forest, yeah.
And, in North Carolina. My nephew went to law school at Wake Forest.
Oh.
Yeah, but he was from Georgia, but he went to law school there.
Yeah.
And I had a niece, one of his sisters, actually lived and worked, and her husband and family in Charlotte. But then, one of them dropped, in fact, she worked for Bank of America.
Okay, yeah, that big bank down there by the
Right.
Carolina.
But, her husband got a job in Raleigh, so they moved to Raleigh, but she sort of telecommutes.
Exactly.
With Bank of America.
My mom was actually, she worked for a chiropractic, so she was involved with surgery scheduling with a lot of like Cam Newton. Jeff Gordon came in one time, and on the sheet it said Jeffrey D. Morgan. My mom was like, Jeff, that sounds familiar to Jeff Gordon. And sure enough, here's some big black tinted one of the big Escalades that come through. She's like, that's got to be him. And they have to go through the front door, but he gained access to the side door so nobody could see him. And he came walking through, and I was like, oh hey Jeff. He's like, how are you? Trying not to cause so much attention to it. But she did Jeff Gordon. She did Cam Newton. She did a lot of the NBA, your big football players and stuff like that. So she was there. Then my dad was actually in charge of the healthcare department in what was that? The Charlotte Metro Hospital or something like that. I think that's what it was. And so he was in charge of the clean department, make sure all the rooms were clean for all the patients that would come through. So unfortunately, they said that they don't want him. They want someone else to come in and make some more money. So that's when they shipped us down to Birmingham. So now he works at the Children's Hospital.
Oh, really?
And he's got this big promotion where he's in charge of the whole healthcare department. So that's pretty cool. So we got a promotion there. And then my mom actually works over at Grandview, not the big one they just built, but she works at an off-site campus, what they call it, for heart patients and, when they have to go through the leg with all the veins. I know how to do that,
Yeah, catheterization.
Yeah, exactly. But that's what brought us down here with Dad's job. So I moved 6 times since I was born.
Wow.
I was born in New Hampshire, so I started, close to Maine, and then I spent the majority of my life in Buffalo. That's when the Buffalo Bills.
Oh, okay.
So.
Well, it's a pretty cold area. So
Yeah. And I was actually going to do my research paper on lake effect snow.
Yeah,
I was
exactly.
right
Fantastic.
on the
Yeah, sure.
right on the lake there. So, anyway, it was Buffalo, and then spent 6 years in Ohio, which was the Cleveland area, just outside Cleveland and just outside Columbus. Now that's for my brother. He was a diehard Cleveland Cavalier fan, LeBron James, and Ohio State Buckeyes. I really can't see that. Because I like the Trojans, the USC Trojans. So I was like, yeah, you're not good that right. I can't do it. But anyway, then we got shipped over to Kansas. Spent a good time there, about 3-4 years. That's where I decided I wanted to go into flying, airplanes and all that. But then when I took my colorblind test, I failed. So I said, you have to have some sort of backup plan because you won't be able to fly an airplane with colorblind.
My nephew, who's a lawyer, he's colorblind.
So I had to, step aside and say, what else I could do in my life? I was working on cars, working on hands. I'm thinking, I'm going to go to school for automotive. And so I spent a couple months there before I had to move to South Carolina. And that's when my brother, he's a big sports fan. So now he's a Wichita State fan, and he likes the Gamecocks. Just being from there. And so
I have a niece, my other brother. She got her. She was working on her PhD at South Carolina. Her major professor just screwed around with her so much she finally went off. She got married.
She finally had enough.
She's not going to work on education.
Yeah. And then my grandmother actually lives, and my grandfather lived in Myrtle Beach.
Oh,
just outside of Myrtle Beach. It's like North Myrtle Beach area around there. And so, a couple times a year we'll go up to see them. We haven't been there, since we're in South Carolina. It's only like a 2-3 hour drive, so we do. But that's what. And then South Carolina, then we came here, and I've been living here. Me and my family lived here for about a year and a half so far. So, we pray, for snow, but we really haven't seen any snow.
You're not going to see much.
It's more like the severe weather, like we had in Kansas. They say if you see like a turquoise blue sky, that means it's hail. And here's the same thing. When you see turquoise blue sky, it's hail. So let's get all the cars inside, make sure that everything else has not damage inside. So it's a good thing that we live there. Now we get to prepare ourselves to live down here for the severe storms. And I work over at Pell City Ford, Town and Country, over at Pell City. And I was like, they said I had to stay here for 3 years to get my master's, but I said, I want to get my 3 years, I'm going back up to New York.
Oh, really?
They're like, why? I was like, snow.
Yeah.
Like, you want to see snow 6 months out of the year? I said, absolutely. I'm like, you guys can't drive in snow down here. You see a snowflake, you guys panic. They're like, no. Go in the store, all the bread, all the milk is gone. They're going to be stuck inside for those 3-4 days. With us, we can drive. As long as you go slow, you pay attention, you'll be able to drive.
And you have snow plows too.
Exactly. Yeah.
They don't have
Down here.
I mean, who would walk it? It would make physical sense.
Yeah, you're down in what it's called the Deep South. Right?
Yeah.
Down here, Deep South. And that's when, somebody said, man, this southern ice is different from northern ice. I said, isn't ice? It doesn't matter which, But I do want to go over my research papers. Okay, if I do.
Oh, absolutely.
Lake effect snow. Because I love the weather. If it wasn't for automotive, I wanted to be a meteorologist and all that. So I'm like, my parents, we were driving through. You ever heard of the town called Greensburg, Kansas? They had that big tornado that went through.
Right. I remember.
So, we went back there a couple of times, and every time we went back there, it was always green. They had green in their name, so they had, solar panels, all that. So just in case another event like that happened, that we would, We use it, resources. And a tornado was coming right down, I think it was I-90, I think. It's a little too many, that's all it is. But there was a tornado up in the distance, and everybody was pulling over the side there, taking pictures. I'm like, Mom, pull over. He's like, no, let's keep going. And she wanted not to do it, but I really wanted to see it just because it was my first time seeing a tornado in real life. I was like, maybe that wasn't the best idea. But then as we were driving through, it looked like cotton. And I'm like, that doesn't look like cotton. And then we got a little farther ahead, and it was just like, oh, it's hail, because that storm that went by all over the ground. Like, we couldn't believe how much hail there was. It looked like snow.
Amazing.
But so it is okay if I do the
Oh, yeah.
lake effect.
Sounds good.
Okay. And with the YouTube, are you gonna have that on Blackboard so I can go ahead
I don't have it there yet. I hope, I'm not gonna have much time tonight.
and
Now, having an infusion tomorrow, so I'll be
Yeah,
sort of out of it. But if I can get it done this weekend, possibly, but if not, I'll get it done.
Okay, I think it's like, you said, 2 pages, I think.
Yeah, 1 to 2 pages.
1 to 2 pages. Okay.
Double space.
All right. Appreciate it.
All right.
So you have a good weekend.
Yeah, you too. My wife works at Children's Hospital too.
Oh,
But she's
it
over
would
at,
be
yeah, she's at Children's Harbor, that
hard.
building, right?
Mhm. My dad actually see the stadium where I think it's like Regents Field.
Yeah.
See, he's on the very top floor, so he could watch the game if he was
Oh,
there.
the new building.
Yeah, the new
Way up
building,
there.
yeah. And they have all those apartments across the street that they start at $3,000. I'm like, you're paying $3,000 for a 1-bedroom apartment. Yeah, it's just for the view because you got the stadium, right in the backyard. That's your entertainment right there. But yeah, he works at a brand new building.
Yeah, Children's Harbor is attached to both the old hospital and the new Children's Hospital.
Oh, it is. There was an old.
It's right there. It's a little squatty building in between the two. There's a crosswalk that goes this way and then one down.
Oh, yeah, you're right.
And it's only like 4 stories at the most.
The old building?
It's not an old building. It's just
Oh, it's called the old.
the old Children's Hospital
Children's
is that's what I meant.
Mhm.
And before they built the new.
Yeah.
But she parks in the parking deck.
Yeah.
You're the older one and walks across the street.
My dad's on the opposite side of that, so he can gain entrance through. He was at the old parking lot.
Right.
But after his promotion, they said, yeah, you get VIP access. You're like, okay, that's fine, I'll take it. So he's on the opposite side, but then he has, his own parking spot and all that. That's fine.
Yeah, called parking at UAB is free.
Mm-hmm. And then there's a couple dents on his when he was over at the old parking deck where they were just slammed doors, and he has a brand new Toyota Camry, so he's like, I can't get a break. But after he got the promotion, he's like, I haven't seen any dents for the last 4 or 5 months. He's like, let's just keep it going.
Right.
So.
And you mentioned Augusta, where my family, where we lived for ever since we moved to North Carolina, was Waynesboro, Georgia, which is just south of Augusta.
Yes.
Next on 25 South. And that's where my parents' farm was. Both of them are dead. The 4 kids have split up the farm, but not really. I mean, they left it to us in the will, but we still operate it as one farm.
Yeah.
And so we have a little 2-bedroom bungalow over there that when we go there, we have a place to stay. And so we go near Augusta, just
Near Augusta. Almost like in the Savannah area.
we're close, right closer to Augusta. Augusta's in Richmond County, just south of the Burke County.
Oh,
We're
okay.
just across the Burke County line. The Richmond County line.
Yeah. And then we would go through Augusta, then through Savannah, because we went through all the tiny little shops there. And we
Savannah's such a nice town.
And then we finally got to the very, very lower bottom of South Carolina. That was like Paris Peak or something like that, I believe. And
Paris Island is
Paris Island.
that's the Marine Base.
Yep, that's what it was. Yep. And then we said, we're gonna go, hit Savannah and then go around, go through Greensville or
There's a Greensboro.
Greensboro.
And Madison. I wonder if you did Madison.
Madison, because it was just a straight shot
through Atlanta.
Through Atlanta, and then we finally we're beach ready. We're at the south end side of North Beach. So then we're like, okay, that's nice. So we need to go south back to Myrtle's Inlet. And I don't know if you heard that. It's a little inlet that has a bunch of fishing and all that.
Oh, really?
Mm-hmm. And we're like, oh, that's nice. So we need to go south. And we finally hit Myrtle Beach. We saw the international airport up to our like, okay, the beach is right there, so we got to be there. So that was the last time we were there. It was like 4.5 years ago. We've been there. Just is all moving and everything. Because I'm going through school. My brother actually goes to the Birmingham campus.
Oh, really?
State. So he's doing the business. He wants to get to sports management, being a scout, and he's working with. He was working with the baseball team over at UAB to get some experience, training, and how to scout players and have them go from this team to major league and all that. So he wants to do football. I was like, good luck. I'm trying to go to a UB football game because they're just starting to get back into the program.
This was our first year back. President shut it down.
Exactly.
And because he was on University of Alabama runs the University of Alabama system. And we're part of that. Three schools, University of Alabama, UAB, and UAH in Huntsville. And UA, in Tuscaloosa, they own all of the board of trustees except for a couple of taking members. And he was a UA fan, not a UAB fan. So he shut us down because we had a coach that was doing really well. And they were afraid they'd be competing. So he shut us down. That was technically the reason. Then the community got together and really crawled back. And he had to concede and let him come back. And the board had to concede and let him come back. So they were out for 2 years. The coach stayed here, even though he didn't have a team. He had only been here one season before. And he stayed, and he's a very good guy. He's very family oriented, and he recruits well and stuff. They went 8-3 this year, I think it was. On their first year back, and however, they lost the ball game 8-4, I guess. So, 11 regular season. So, or something like that, maybe off a little bit, but he beat teams. They were supposed to be bottom of the conference, and they were very close to the top of the conference. So he's a really good coach. Not at the level of Auburn and Alabama or Carolina, but at their level, he's something quite well. And Karen, my wife, said she works at Children's Hospital, but she's a UAB employee. She's in the Department of Pediatrics. And they share a facility. So
she's with the sick children and all of that.
Yeah, well, actually, she's an epidemiologist. She studies diseases, and she uses data from there. And she works with the doctors who are there too.
Who do the procedures on the patients.
Yeah. She doesn't do any procedures. She collects data and puts the data together and reports it. And she's finishing up her 25th year, I think. So she'll be eligible to retire sometime soon. Already eligible, but I want to work for a few more years. Probably till age 67 now. So if the health holds out and everything else, I'll have to make it 3 more years. Then I'll be ready. I'm pretty close to ready to retire now, but I think I can make it. Good deal. I'm sorry to hold you up.
No, it's okay. I got my next class at 7, so it's okay.
Oh.
Like to eat.
Okay, right. What class is that?
Math, 100 with Mr. Brazil down in.
Oh yeah, he's good.
Down in 160.
Yeah, he's quite good.
I like him. It's my second year, second time hit with him because I had for
Oh, 98, I'll say.
Yeah.
All right, good deal.
See ya. Good talking to you.
Uh-huh.